Thank you everyone for joining today. We are going to go ahead and get started. So welcome to day one of the Upcycled Food Foundation's Scientific Community Global Research Symposium 2. We are excited to be back together and gathering with a phenomenal array of speakers from all corners of the globe today. And I'll do a brief mention of welcome and some housekeeping, and then we'll dive right in. So pleased to be here, Amanda Oenbring, CEO of Upcycled Food Association, as well as Executive Director of the Upcycled Food Foundation. And joined today to help work through day one is the fearless queen of upcycling herself, Dr. Lara Ramdin, who has been so instrumental in both bringing together our global scientific community as well as helping kick off these symposiums. So big thank you to Dr. Lara. We'll hear from her soon. And also grateful for my colleague behind the scenes, Bo, as you're moving through today. And if you're joining us tomorrow, they're available behind the scenes if you have any questions. So do reach out to info@upcycledfood.org. So we are here. 2025 has been a momentous moment for the Upcycled Food Foundation in service to the Upcycled Food Association. So we are just about 6 years young as an organization, rooted in helping grow the upcycled food economy. And over the lifetime of our organizations, really helping to propel the innovation, the science and the research and the next generations of who are helping this global momentum move further. So as part of Upcycled Food Month, which we celebrate each June, we kicked off this global community this June. And we're so pleased to have 22 speakers over 11 hours from 10 countries in June, our first symposium, and we had so much fun. We decided to do it again. So here we are, really pleased to have you with us. Whether you're on the line today or watching this recording in the future, there was so much amazing insights and just different perspectives that were shared in June, and really looking forward to the next hours and the next day ahead. So just a couple housekeeping notes as we move into our sessions. Just as a reminder, this webinar is being recorded. It'll be made available to attendees as well as UFA members. So we know the schedule is packed and the time is long. So if you need to come and go from the link or come and go from sessions, know all that will be landing in your inbox once symposium is concluded. We do have a lot of different speakers joining in an efficient schedule. So we do welcome your questions all throughout presentations. Please do use the Q&A feature of Zoom, and we'll be monitoring that in the background. And as time allows, either addressing questions at the end of presentations or in follow-up with our great speakers. And again, we have so many different minds joining and meeting today. We'll make sure to include speaker information and follow-up so you can continue to connect with folks you'll be seeing here on screen. So with that, want to point you towards our landing page available here at the QR code, or my colleague will drop it in the chat just to see the flow of our speakers today. So you know kind of who is next, as well as in the essence of time, we're including their speaker bios and information in the landing page where you signed up for this event. So do welcome you to read more about our speakers there. So with that, we are going to dive into just a little bit of an overview to get us grounded before we welcome our first speaker. I am pleased to share just a bit more about UFA. If you are new to our organization or potentially new to the movement, we've got folks from all over the world joining and excited to share. So we'll just move through a couple minutes of getting grounded in some of our core concepts. So we are here as the Upcycled Food Association, as I mentioned, that got its start about 6 years ago, really with a core goal of helping bring shared language and shared resources to this movement of upcycled food. And really the first founding premise that we gathered with some of the experts you see here mentioned on screen was to define upcycled foods. So the 3 pillars that have been core since our founding was upcycled food using ingredients that otherwise would not have gone to human consumption, are procured and produced using verifiable supply chains, and have a positive impact on the environment. Why is that so pivotal today? Today, September 29th, is the 6th annual International Day of Awareness of Food Loss and Waste. So feels so pivotal to be gathering with this global community and really using our shared knowledge and our global resources to help address the challenge and the opportunity that is food waste. You all are invested in this, you know these numbers well, definitely see so much potential in addressing what is currently being wasted and making sure that can be transformed into value. Some of the foundational resources that we rely on specific to the US, but US nonprofit ReFed does a deep survey of food waste solutions, and we always track really closely how upcycling, or byproduct valorization in their terms, is really helping to move the needle among food waste solutions, both in terms of climate impacts as well as the social and human benefits too. So if you're not familiar with their insights engine, I invite you to explore the link in the chat, and those numbers are up to date as of 2023. Really, what grounds us is looking at the potential for upcycled food products in such a wide variety of implementations, and really excited to hear a wide range of those in the upcoming hours. Often folks think of upcycled food in traditional food ingredients or products, but really the use is spanning so much beyond just CPG into the pet market, cosmetics, home and personal care, and a lot of really interesting things you'll be hearing about. Why does this matter so much? We know it, we love it. What we lovingly call the U at UFA was the US EPA's updating to their wasted food kind of taxonomy. End of 2023, they elevated upcycling to an equal value solution alongside donation. And that is really pivotal in the broader equation of food loss and waste that we're talking about. Wanted to bring your attention to one other just released resource, and that Project Drawdown also does a really deep dive of scientific solutions across combating the climate crisis, and they've just updated their resource in a phenomenal calculator of really looking deeply at all their solutions, and invite you to explore their food loss and waste page. So that's just a little bit about us at a high level as the Upcycled Food Association, our membership-based trade association, and the Upcycled Food Foundation, our 501c3 in service to the association. We exist to accelerate the upcycled food economy globally, unleashing the innovation that we're here to talk about today and tomorrow to ultimately stop food waste. We do that in a couple different ways: collaboration amongst our members. Here we are today, really zooming in on the topic of research, but then we also span being a voice for policy and broader education to industry stakeholders as well as consumers. In the almost 6 years of the network growing, we are truly global. There's members spanning from R&D, innovation and infrastructure, CPG, ingredient companies, startup to multinational scale, and especially a heartbeat of the community is who is gathering here today: our students, our individuals, our institutions that are really driving the science forward. And that's what makes us unique, bringing these diverse spectrum of perspectives and voices together and really understanding how we can do more together than we can alone. So a little bit about what that journey has been. You're probably, many of you, very familiar, small beginnings, launching Upcycled certification in North America in 2021, and then fast forwarding to today, really how are we bringing the global community together? Upcycled certification has been momentous within that. So we helped develop the standard, which became Upcycled certified, really closely in partnership with the certification body Where Food Comes From, all along the journey of those years. At the end of 2023, Where Food Comes From acquired Upcycled certified. So if you or somebody is looking to get an ingredient or product certified, you work directly with them, and really celebrating the growth of certification over 100 participating companies, over 800 products or ingredients, and seeing some really exciting momentum in terms of the categories of where upcycling is coming to light, as well as being in use globally now. Part of what we do at UFA and UFF is to really help keep a pulse on these measures. So this was one piece of insight from our annual member meeting earlier this year presented by Nielsen. And this chart is so fascinating to me, looking at a 4-year time horizon in the US, the momentum of different claims, and then doors and stores. So really so encouraging to see Upcycled certified specifically, as well as Upcycled and zero waste seeing a lot of attention. And we're going to hear about that today across, what are the innovations that are helping found companies or specific products, or the opportunities to take existing formulations and integrate upcycling into what is currently out there. That's something we celebrate every day at UFA, though especially each June as we celebrate Upcycled Food Month. So I'd invite you, as you hear insights and inspiration today and want to keep in touch over the course of the coming days, we have a public newsletter that is bringing all these headlines directly to your inbox. So I invite you to check out that link, as well as you're participating in the conversations today and tomorrow, thinking about what the role for you could be in our community. We have everything from student and individual memberships through to organizations and companies. So a really wide variety of ways that you can be participating and involved in the days ahead. And this is just the beginning for the scientific research community this year, and really excited to, in partnership with the minds that have helped found UFA and UFF, be carrying that forward. So we're going to be hearing a lot of conversations in the coming minutes, as well as here today and tomorrow. And this is an example of convenings that we do regularly throughout the course of time. So if you end these 2 days and are hungry to listen and learn from some more, I invite you to enjoy this series that we did to mark our 5th year anniversary just about a year ago now. So those recordings are available, as well as a wide variety of Upcycled Food Month recordings and other resources, which you can always find at upcycledfood.org. Hopefully that helps ground you into the who and the why and what that we are today. And I am so pleased to introduce and bring on stage and invite the mind that brought this all together. So without further ado, Dr. Lara Ramdin, welcome. Let's kick us off.
Hello. Yes. So it's all my fault. That's that's what I get from that. Welcome to our second scientific symposium. Indeed, it's quite remarkable that we had 22 speakers from 10 different countries in the first session in June during Upcycled month. And actually, there were lots of people who wanted to take part but couldn't take part in June for one reason or another. So we're delighted to be able to do this a second time and make sure that everybody gets a chance to share their research, and also highlights essentially all the science and technology that's burgeoning in this space. It's also poignant, I would say, that in the end, this second scientific symposium is on this day, which is the International Awareness Day for Food Loss and Waste, run by the FAO, in order to bring light to and highlight SDG 12.3, which is reducing food waste. And I spend a lot of my time thinking about food waste, talking about food waste, talking about how we can reduce food waste. So if this is another forum in which we can bring people together to accelerate collaboration and do more in the reduction of food waste, then it can only be a good thing. So I'm not going to talk for too long, and I'm going to go ahead and introduce our first speaker. Continuing on the theme of a truly global scientific conference, both in June and this time in September, we're starting with a speaker who is Ecuadorian, but is representing both RMIT University and Adger University in Norway. And he is a PhD student, Juan Jose Cardenas, is kicking things off with a keynote. I have the opportunity to meet Juan Jose through another colleague, another friend, Gabriela Alvarez, who's based in Ecuador and leads food product development and food innovation in that country. And Juan Jose and I will actually be sharing a stage together in Ecuador in a couple of weeks to talk more about food waste reduction and circularity between us, along with Gabriella as well, and how it can be used to drive innovation. So I'm looking forward to that. Juan Jose, welcome to the Upcycled Food Foundation Scientific Symposium. We're delighted to have you, and also delighted for you to kick things off. Over to you.
Thank you, Dr. Lara, for this incredible introduction. Also, Amanda, thank you very much for uh, all the organization behind this amazing symposium, and also to all the people around Upcycle Food Association that I don't have the privilege to meet them yet, but as an early career researcher, it's an amazing place to be in order to share some little findings, because as you know, the amount of research done in food waste and the proportion that we contribute to this as a PhD candidate is not as much as we want. However, are the ones that actually will enrich at the end of the day the global agenda. So thank you very much for this opportunity, and also thank you very much for all the panel members that are here. I'm so grateful to be sharing the stage with you guys. Without further say, I will start my presentation, and I will share my screen, and just let me know if you can see my screen.
We can see it, Juan Jose. And if anybody has questions, please do put them in the Q&A section or in the chat. Thank you.
Okay, so let's do this. In honor of today's date, food waste is actually something quite crucial. And I would like to start by talking a little bit broadly about the problem. And as we can see, climate science has informed us that the planet is warming and we humans are the cause of that. However, if we, based on the project drawdown, if we sum all the cities and suburbs all across the world, it occupies 1% of the Earth's land. However, agriculture takes roughly the 38% of it. In other words, food is dominating us. Inside of this system, food contributes to around 22% of the global gas emissions. And on top of that, 30 to 40% of food is lost or wasted. However, the last piece is a painful one, because all the food that's already wasted is already occupying land and energy. However, this can be avoided from the start, yet it still consumes resources before ending in the bin. In this segment, or in this regard, it's important to understand that there has been three main clusters around the solution that has been gaining a lot of popularity over the last years. These are suboptimal foods, also known as misshapen products or near to expire items. We also have upcycled food, as the one that we already know based on the attendance and the speakers over here. And also we have promote leftover reuse. However, here's a key point. Promotion of these main solution clusters has helped gain attention, but evidence is clear. Meaningful change isn't about promotion alone. It's about getting acceptance and then sustaining the action over time. So in that regard, yes, we have improved processes, products, and communications towards sustainability. However, based on food waste research, many programs still aim to inform. Fewer truly engage. Studies that deeply map the consumer inner dynamics are comparatively limited. Why I bring this to the table? Because Based on what I have been researching, the idea is not to invent something new, rather to adapt what we already have. What I try to say by this is that marketing frameworks have shown us a path forward. When we truly understand consumer, we can reuse the wheel across terrains. We don't need to reinvent it. We need to fit it. Right timing, right context, and right identity. And based on this insight and on my research, there has been some insights that I have found focus on four clusters groups of consumers. The first one, household audience. What happens within household audiences when we talk about food waste? They live around busy weeks, and busy weeks push people into automatic mode. Planning slips, promotions are misjudged, leftovers are forgotten. The good provider identity favors abundance over restraint. So edible food slides towards the bin. The second group, students. There are two patterns here that dominate among students. First, time pressure. Quick and low effort routines squeeze list making and reuse. And the second one, sensory rejection. If the food looks or tastes off or just doesn't fit the standards of the student, they are left uneaten. However, something that helps promote these two insights faster is the lack of food literacy. Supermarket shoppers. Beyond the ugly looks and date label confusion, social image matters. What do I mean here? People avoid near expiry or misshaping items so they don't look stingy or cheap. This stigma is actually a real barrier. And finally, among online consumers, for upcycle or surplus offers, there are a lot of doubts centered on the taste, on the safety, and the nutrition. However, acceptance of these type of products are different across demographics. For example, generally high young users accept more this type of a solution or proposal. As you can see here with these main insights, with the introduction stating that we need to investigate a little bit more on a specific content, we can see that the focus of the consumer cannot be generalized. However, has to be more tailor-made or specific. That's basically the core of my research. So the pivot here is simple. Move people from awareness to engagement and keep them with a considerably little, low friction and high relevance. In my study, we are using the consumer engagement framework as the lenses to categorize and help the consumer connect better with this solution. For the ones that don't know, the consumer engagement is a multidimensional framework that tackles three main points. The first one is cognitive, second one behavioral, and the last one emotional. So it's more connecting people to the think, feel, and do. When we use the consumer engagement framework, we start to discovering that we can clusters the solutions that we have discovered for food waste into a system that can be grind together in order to ease the use of the consumer when they are implementing. In this line, we have so far, because the research is not done yet, we have so far integrate three systems across where consumers can engage in consumer-facing implementations. The first one, digital platform scan folding. So basically, what this system does is connects products data to people routines, so the right next step appear exactly when they need it. As an example, retailer apps can auto surface near expiry products and create bundles with transparent discounts. Also, at the same time, send use it tonight prompts after purchase and often tap recipes that can help the consumer. The second system are educational toolkits. What does it what it does this system encompasses many implementations, but the main goal is to convert motivation into ability with simple tools and also micro-learning. For example, Use Me Up Kit, where we can have visible markers, storage guides, and 10 minutes recipes, and also promoting this in campus model so that we can turn possible food leftovers or possible food waste into dishes. And finally, eh, information framing and delivery. What does what it means? It means adjust micro copy and placement where choices happen to remove identity risk and ambiguity. Okay, so here comes a mixture of communication, prompting, and allocating correctly the messages as in order to, for example, in the case of upcycle or food waste promotion, when people feel that they are stingy or cheap, we can reframe that by communication strategies such as smart saver, fresh tonight. And therefore, in this slide, the idea is to start to switch the structure that of how consumers feel when they surfaces or when they interact with these products, and using the communication as a core element, switch the ambiguity within their heads. Finally, in order to end, I would like to recognize the following point. And the following point is that people don't waste food because they are the villains. However, they waste food because it's the easiest path, because the easiest path often leads there. Our job, or the main structure of my research, is to retune the path so the easiest choice is the lowest waste, and often the idea is to create consistency among them. I would like to finish stating the quote of Buckminster Fuller that says, "You never change things by fighting the existing reality. To change something, build a new model that makes the existing one obsolete." Consumer-facing implementations, system-aware structures aligned with engagement are that model. Let's use them to move from awareness to action and keep it that way in the long run. Thank you very much for your time.
Thank you so much, Juan Jose. I am interested to understand this research that you're doing. We had End Food Waste Australia in our first symposium in June. How have you, and I think you're doing some work with them, how have you used this research in real terms, in real life?
There are many consumer-facing implementations they are using. Consumer-facing implementation can also be known as interventions. So the idea is to test these interventions and to see the level of engagement. Because at the end of the day, the core of my research is not only to see what has been done, rather to evaluate what has been done towards the consumer engagement lens and see how this engagement is properly fitted according to the framework that I'm using in this case. So answering your question, Lara, the idea is to use the platform of Endways and Foodways Australia and see the implementations they have done and evaluate the engagement level they are creating in the long run and see possible changes that can fit the system in order to achieve this amazing goal of engagement.
Can you talk about anything that you think has been particularly successful? Because I certainly use them as a gold standard, especially when it comes to something that's consumer facing, which if you work in upcycling is essentially a big challenge, right?
Yeah, totally. There's one implementation that I quite like a lot. Is one done by Mark Bullitt, a researcher at Australia, and he generated one in collaboration with an organization in Australia called Oz Harvest. They create a masking tape, and this masking tape is used to tag food in your refrigerator, so you can give yourself some prompts in order to eat the leftovers that you have in that you have stored. For example, this masking tape has two elements: use me up, eat me up. So the idea is to base use this prompt to help the consumer to eat the product that they have when they open the fridge, and also to label the possible ingredients that they can use in future meals. However, this implementation was not just only the sticker alone. It comes with an informational package that help consumers to understand how to use this intervention, and also there were diary logs where they actually comment about how they feel when using this type of intervention.
It's amazing to me that something as simple as a bit of masking tape on a food can actually change people's behavior. Did they see a significant reduction in waste? You know, what was the percentage of people that really saw significant behavioral changes?
I will lie if I will give you the exact percentage. However, in broad terms, there's a significance in the change of behavior, because this prompting, according to their logs of each consumer, actually help them realize that there's food that need to be eaten. Also, this is quite linked to their economy, because most of the food that they were taking from the fridge were for the next day, so they don't have to buy lunch the next day. At the end of the day, what I'm trying to say is that more than the percentage itself, we're among researchers, and unfortunately, I don't have that data, but I can come to you and I can give it to you and to everyone that needs this. But the main insight is the following: is how simple tools can actually shift the automatic mode that we have by only opening the fridge, prompting ourselves and realizing that we can take another action, that we cannot that we can actually help those ingredients, that food, not go into the bin.
There's a few more questions, Juan Jose, which is great. We're generating some discussion. So you represent two different universities, RMIT and Adger University, Australia, Norway. Is it fair to say that behavior and also cultural attitudes toward food differs greatly from that in the US, say, and therefore if you were to repeat the masking tape study in Australia, it would be quite different? Or would you have to use a different kind of nudge in America versus instead of this masking tape idea?
Okay. I think that the demographics of the United States there's a lot of inputs in this formula. due to the migration that they have, due to their cultural influences, due to the lifestyle, because the American lifestyle is completely different as the Australian and is completely different as the Norwegian. And also because we're doing across sectional studies, and we're comparing Australia, Norway, and Ecuador, I can say that perhaps, Lara, we can adjust somehow the nudge, yes, but the core principle of giving you a heads up at the moment of open the fridge, it's something that can be replicated among different contexts.
Yes.
I think that it's not about changing the nudge. However, is recognizing the simple act of open the fridge and give you signals while you're open the fridge. However, the way how we codify that those signals in our brain, yes, cultural influences make this vary a lot, a lot, a lot. And as I said before in my presentation, delving into the consumer behavior itself, it's something quite critical, because there's a lot of things going on within inside the mind of the consumers. And despite the fact that they open the fridge and they receive the signal, this could be a win or could be a lose, depending on what happened to you in your daily life. What happened? I mean, this is amazing, and with this, I want to conclude the answer. What I'm trying to say at the end of the day is that perhaps, based on the evidence, the core structure of consumer-facing implementation can be replicated. Nevertheless, a deep understanding of our audience is critical, because the deep understanding of our audience will be the guiding light in order for us to adjust these implementations and to evaluate the future outcome of it.
Excellent, very good. A question from my colleague Jonathan Kershaw. He is a professor at Brigham Young University, and we've done some work on framing language for Upcycle Foods together. He would like to understand if you have any examples of implementation strategies that you've studied.
Yet, dear professor, thank you very much for your question. Yet, the strategy itself, there has been a lot of implementations done, but the way how we are segmenting and clustering them, that's the core idea of the research, and we are getting in there. We are working in a meta-analysis in order to see how we can give an example of the functionality of the clusters at the end of the day. But so far, I have examples of implementations, I have the procedures of the implementations, yet the functionality of the clusters of how I presented are not ready to present in honor of the truth.
Okay, very good. It says Jessica Volker, but I'm hoping it's my friend Jessie, who I've known for a long time, who actually works on a cosmetic brand, which also looks at, it's called No Planet B, and her and her husband have developed this brand and have used are using upcycled ingredients in their products. So she's asking the question, and by the way, this is a question that we ask ourselves all the time, but interested to get your point of view on this. Jessie thinks that waste and upcycling are two different things, and the consumer sees them as such. So when we talk about food waste, what they really think about is the waste that they put in their bin, right? And that's a bit yucky and disgusting, and sort of elevates the disgust factor in your brain. But really what we're talking about when we're talking about food waste reduction and upcycling is at other parts of the supply chain and earlier parts of the supply chain, which you alluded to in your presentation, where the food itself isn't yucky, necessarily, but maybe just be a bit, wonky or actually and so Jesse's asking, in your experience and your experience of understanding the consumer, should we be avoiding putting everything all in one bucket? I think yes is the answer, but I appreciate your thoughts on that. And is the job to be done actually to separate ourselves more from what goes in the bin at home and focus more on messaging around other parts of the supply chain as a result of that?
That's a really good question.
She's a smart woman. I would expect nothing less.
Yes, she is. Yes, she is. Okay, should we put everything in one bin?
Well,
Based on
from a language and engagement perspective, I think the answer is no, right? The answer
yes,
is
the
that
answer is no.
from based on all the research, including yours, we have to do a better job. If our goal, our purpose here today is to talk about how to valorize what is wasted at different points in the supply chain and put that back into the food system, then we have to do a better job of separating ourselves from what consumers perceive as food waste at home, right?
Mhm.
And
Okay.
that's one thing. And then so I agree with that, Jesse. I think Juan Jose agrees with that. But then how does language and nudging and engagement evolve then, if that is the case?
If we not put it in the same bin, or if we put it in the same bin?
Mentally, if we don't put it in the same bin, if mentally we're trying to compartmentalize
Perfect. Okay.
food waste that comes from other parts of the supply chain versus a consumer's behavior at home.
Okay, there's this theory, the long tail marketing niches, okay, which talks about basically about niches and their potential. For example, why? What I will tell you why I starting the answer in this way. Just give me a second. But what I'm trying to say basically is that based on the long tail marketing niches, uh, there's a lot of evidence telling us that on niches there's a lot of more than reputation. There's a lot of consistency and engagement within the consumers. For example, we have Netflix, but if someone is super into anime cartoons, Japanese cartoons, there's a platform called Crunchyroll. Okay, and despite the fact that we have anime reproducing on the platform of Netflix, someone that truly values and is super engaged with anime will buy their subscription into the other platform. Therefore, these long tail marketing niches talks about more than engagement is how we can make our consumers becomes our tribes, okay, our community, and this community will sustain us in the long run. Why do I bring this at first? Because I think that when we start to understand the fact that not one size fits all structure among the sustainability domain, we will find a lot of insights that will help us thrive. In this case, when we segmentize, when we make the segment a little bit more narrow or close, we can jump into more techniques and approaches that will foster engagement, and more than engagement, co-creation. And that's a critical point over here, because sometimes we as researcher, we underestimate the power of society. Okay, and sometimes we often rely a lot on theories and theoretical backgrounds. But in order to answer your question, I think based on what I've been researching on the insights that I have gained, I believe that once we start to make these segments more robust, and when I'm saying more robust is integrating the element of engagement, we will receive more insights than we will ever imagine. And these insights will be the responsibles to keep the community tight. However, a community, we should make baby steps. And these baby steps will be starting from small to big. In small to big, it will be amazing to start this division and framing this division among the consumers that actually feel in, consumers that actually feel this information that resonates within. Okay. And when we trigger that, I think we discover the missing piece and the holy grail, and we can save the planet. But this is my presumption based on the research done. So in order to close the question, I will say make separate bins, yes, because in this separation we can actually cover more, and more than cover more, perhaps in this distinction we can find linking points that at the end of the day will help us in the future gather all together.
Well, you've given lots. You mentioned it briefly, but there is no one size fit. There's clearly no one size fits all, right?
Yes,
So
indeed.
whatever system you have to approach, you have to have the flexibility to adapt for different consumer demographics and cultures and behaviors, right?
Exactly.
You feel through your research that this is ultimately possible.
It's possible, yes. Economically feasible, let's see.
Well, that's the key, isn't it? Because
Yes.
otherwise, I think if it's not economically feasible, then it doesn't get adopted, Juan Jose. And that's when we see things in our business, in our food waste business. I think that's when we see things falling over, as in, just sort of grinding to a halt, right?
That's the main core of my research, to prove not only the feasibility of the theory rather than the practicality in economical terms, because the idea is to show that this is a new business model, and this new business model will bring a lot of not only economic benefits, but also social and environmental benefits. But yes, Lara, that's the challenge. Indeed.
As we close this session, I just want to share a comment that Shannon put in the Q&A, and she is suggesting that instead of separating ourselves from residential waste, so what consumers put in the bin at home, should we not take on more of this responsibility for how single stream composting works? Now, I don't know whether they have composting in Ecuador, Juan Jose, but I'm sure they have it in Australia, and it's becoming a bigger route to enabling food waste reduction here in the US. But in the US, it's still behind a lot of different regions and countries. Shouldn't we also be using a coalition approach to systematizing all of the commercial supply chain waste to value flows instead of relying on company by company choices? We can develop a vendor approach that outsources these strategies to avoid forcing companies to change core processes and profit efficiencies and get approvals at the vendor handshake level this way. Shannon, I think the idea definitely has merit, but I think you might be talking about a utopia that doesn't exist. The idea that we somehow, before it gets to compost, separate out the things that add value and the things that perhaps aren't as valuable, and having one aligned approach certainly makes sense, I think, and is certainly a no-brainer. But in this country, we can't even really sort plastic out properly, which I think has been embedded in many different countries over years and years and years. So I think to then try and get a better infrastructure on food waste would seem like a very tall order. That's just my personal opinion. I think, Shannon, though, you raise an interesting point, and I don't want to leave it there, because I think we should come back to it and have more of a debate about this later on. But in the interest of time, I'm going to close this session with Juan Jose, and move on to our next speaker. Juan Jose, it's been such a pleasure to have you. Do you want to say something?
Yeah, Lara, I think I just want to mention this super briefly. There's one thing that we often lose sight, which is the fact of that we operate in a system called business as usual. That is something crucial. That is something crucial because we are sustainability activists, sustainability researchers are competing against with what and how the market is already structured. There are plenty of solutions that are feasible solutions. However, if we miss this fact of the system where we operate, I think that's a crucial thing that we should all consider at the end of the day. And I thank Donella Meadows for giving me that input. She's not here with us anymore, but Dr. Lara, thank you very much for your time, and the Upcycled Food Association for this chance to be able to speak and share my thoughts. If you need further information of my research, please contact me, and have a wonderful day.
It's been a great way to set up today's session, Juan Jose, and I'm sure we'll generate a lot more discussion as we go throughout the day. Thank you so much. And now we're moving over to our first speaker from Cornell University. I want to say a huge thanks to Rajni Aneha, who she and I have been talking about this for at least 18 months, about arranging a session with Cornell University, who are, I would say, one of the leaders actually in upcycling, have created a kind of upcycled hub almost at Cornell University, and a hive of activity when it comes to science and technology in upcycling food. And I'm delighted to welcome Matt Smardz. And I found out that Smardz this morning means tasty in Polish, so he is obviously in the right place. Matthew, over to you for your session. We're starting a little bit early, but that's okay because it leaves more time for questions afterwards. So over to you.
Of course. Thank you so much for having me. Hi, everyone. My name is Matt Smardz. I'm a PhD candidate in Pat Gibney's lab here at Cornell in the Department of Food Science. And my personal research is on protein engineering and strain engineering. And I do a little bit of grape pumice valorization work. But today I'm here to introduce the department and the people from the department who will be speaking. And so our department is situated here at Cornell between both campuses, the main campus down in Ithaca, New York, and the Agritech campus up in Geneva, New York, about 50 minutes to an hour north of here. And so just a quick overview about our department. We have an IFT approved undergrad food science program, and these numbers were from last year, so they've kind of shifted a bit. But there's about 132 students between food science and viticulture and enology, 106 students that are in the China Agricultural University / Cornell dual degree program. We have about 100 to 110 grad students split between the professional Masters of Food Science, research MS, and PhD students. And we have about 26 faculty, and as well as about 100 research and extension staff, and about 15 million in total research expenditures. And on the right, I wanted to highlight some of the student clubs here at Cornell. As undergrads and grad students in our department, involvement is really popular. And we have clubs that span all sorts of different interests. So this is the Upcycled Talk, so the Upcycled Food Club, as well as Big Red Brewing, which is a grad student brewing club who've done collabs. They've done upcycled food brews. The Product Development Club, as well as our grad student organization, and my personal club that I'm the president of, the All Protein Project through GFI. And so in our department, we have a range of specialties between the two campuses. We have disciplines from microbiology and food safety to processing and engineering, fermentations, developing active packaging, looking at foods for health and ingredient functionality, and then of course sensory science and flavor chemistry. And our research and extension projects also cover things like dairy products, fruits and vegetables, and craft beverages. something housed here at Cornell that goes across across departments on campus is the Cornell Institute for Food Systems, which is headed by Rajni. And it really looks to build public-private connections. And you'll be hearing from two of the faculty fellows here today, Elad and Kay. And one of the initiatives that SIFS puts on each year is the Food Hackathon. And so thank you to UFA for supporting the Food Hackathon. The Food Hackathon is a really great way for students to get involved and really think about how they can, when posed with a problem, build a solution. And it's very popular. Every year there's a wait list. And if you scan this QR code, you can kind of see the highlight reel from the 2023 event. We've been having it every year for a few years now. And it's really popular. If anyone's interested in getting involved, you can check out the website, hackathon.cornell.edu/food. And it's just a really great way to engage students. And some of those teams go on to enter product development competitions in all sorts of different fields. And so to give a run of show of who will be speaking today from Cornell, you'll be hearing from Dr. Elad Tako, who'll be talking with his lab members about the value of fruit skins, transforming food byproducts into health benefits. And then you'll be hearing from Dr. Kay Wang, and she'll be talking about innovative and translational research and converting food waste into byproducts and bioplastics. And then you'll be hearing from Dr. Shukla, who's a postdoc. He'll be talking about food technology to enhance upcycling, going through some case studies from New York State. And with that, I want to thank you all for being here today. Go Big Red, and I'm happy to turn it over to Elad and his team.
For the uneducated, Matthew, what does Go Big Red mean? Apart from the chewing gum?
It's our chant. I'm a big hockey fan. Cornell hockey's very popular, and that's one of the many chants you can hear at Line Rink.
Oh, I see. Okay, thank you. Thank you for letting me know. So welcome to Elad. We're right on time, I think.
Hello, can you hear us?
Yes, we can hear you. I can sort of see you as well. You're in a conference room, standing up.
Hi, everybody. I am here in our meeting room, a conference room with my team that will participate in the presentation today. So thank you again for the invitation to talk about our research in this space. Today, we're very excited to be here. So as the title suggests, we're going to discuss the value of fruit skins, transforming food byproducts into health benefits. As was mentioned, I'm Elad Tako, and I'm associate professor at the Department of Food Science and Technology here at Cornell University, in main campus in upstate New York in Ithaca. My lab or my research is focused in how food dietary ingredients, including plant origin bioactives, how they affect intestinal functionality and morphology and microbiome in health and disease circumstances in vivo. We're using a very unique in vivo model that I will be presenting today. Just so it's connected here. Sorry about that. Okay, so to start, as we heard, each year, millions of tons of fruit byproducts, skin, seeds, and pumice are generated during food processing. Traditionally, much of this material has been treated as waste or used in the low-value applications. Yet, these byproducts are rich in bioactive compounds as polyphenols, fibers, and micronutrients that hold remarkable potential to support human health and contribute to a more sustainable food system. Today, we will discuss how research at the interface of food science, intestinal function, physiology, and sensory and microbiome is uncovering new ways to transform fruit waste into value-added health solutions. We will explore both the promise and the challenges from understanding molecular mechanisms to developing innovative processing methods to bridging the gap between laboratory discovery and real-world impact. Ultimately, The central question guiding this work is how can we turn fruit byproducts into a scientifically validated, sustainable interventions that benefit both human health and the environment. With that, I would like to introduce my lab team members that will participate in our presentation this afternoon. Graduate students Matthew Pataki, Melissa Wang, whom is also the president of the Upcycled Food Club here at our department, Peter Gracie, and Elliot Dugan. What we will do today is to provide a brief introduction of the subject matter. We will discuss our research models and also highlight how we use this model in the context of the grape pomace work that we have been conducting. We will then shift to other pomace ingredients, specifically a case study, sensory study that was conducted with apple pomace. We'll then discuss how we leverage the research that we conduct into impact, and then we will conclude and offer next steps. And with that, I would like to invite Matthew Pataki to continue.
All right, hello everyone. My name is Matthew Pataki. I'm a master's student in the Tako lab, and I'm going to be setting the stage here. So many of you have probably heard the expression that an apple a day keeps a doctor away. And that's actually because there's a lot of nutrients. It's not due to what's in the flesh and the juice that we take out of the fruit, but what's in the skins and stems and seeds. There's a lot of powerful compounds in these parts of the fruit that contain antioxidants, that have anti-inflammatory properties. And a lot of what we're going to be talking about today are these health-promoting bioactive compounds. You've also probably heard the expression that you should eat a variety of different colored fruits and vegetables, or you should eat the rainbow. And on the right here, you can see an image that is a gross oversimplification of what these different plant compounds do. But the point that I'm trying to make here is that the compounds that we'll be discussing are actually what give fruit their color. So the red fruits have a little bit of a different bioactive compound composition than the green and the purple. So it really is recommended to eat a variety of different colored fruits and vegetables for a good reason. And hopefully by the end of the presentation today, you have a better idea of why. Now, as I mentioned earlier, these are primarily concentrated within the skins of the fruit. So when we make juice, like apple juice, grape juice, wine, orange juice, the pomace, which is what gets left over, often ends up going to waste. The example that we're going to discuss at length today, especially through the research that we've conducted, is on grape pomace, which is the leftover skins, seeds, and stems from winemaking. And globally, there are more than 10 million tons. We want to minimize them. Oh, okay. Globally, there are more than 10 million tons produced in the world. Now, despite this being the most nutritionally dense part of the grape, it often ends up in landfills, and producers are paying more than $50 a ton just to dispose of this in New York State. This image you can see here was taken last Thursday. When we went to a winery, there's 3 large apple crates filled with grape pomace, totaling about a ton. Now, if we went to the winery and made 83 trips in a day doing this, filling each tote, and we did that for an entire year, we would be able to collect all the pomace that's produced in just New York State. There are 30,000 tons of pomace produced in New York State alone, which is why we've really latched onto this research. And not only is there a lot of nutrition to salvage, but grapes also have one of the highest rates of greenhouse gas emissions when they decompose. So you might be wondering, why aren't we just using this as fertilizer? Well, in the quantities that we're producing it, they don't necessarily do our environment any good, and they actually produce a lot of greenhouse gas. You can see on the chart on the right that grapes are actually the second highest fruit when it comes to greenhouse gas emissions, right behind bananas. Now, through our research, we've been able to demonstrate that this is nutrition worth saving. And I'm going to pass it over to Melissa, who's going to go into some of the research we've conducted. Or actually, beforehand, Elad is going to come and talk about the models.
Thank you, Matt. So just to highlight the models that we use in our research, we're using a very unique in vivo model that we have established and validated over the years, and this is the gallus or the chicken model. The approach that we're taking in vivo is to take advantage of both the post-hatch period, where we can design long-term feeding trials that allow us to assess a specific ingredient, for example, a bioactive, and or a specific dietary composition, and by that to investigate how the diet that is tested is affecting nutrient absorption and bioavailability. Also, to investigate how the diet is affecting gut health and microbiome changes. And when I say gut health, I mostly talk about the intestinal morphology and specifically of the brush border membrane, which is the digestive and absorptive surface in the small intestine, and also its functionality, meaning the gene expression of various proteins that are associated with food digestion and absorption. And more recently, to investigate how the diet is also affecting muscle growth and development. We do that both in healthy conditions, but also we're able to induce specific disease, anywhere from low-grade inflammation to conditions that are much more significant. On the right, you can see some examples of our published work over the past 5 years and by utilizing this model. As I mentioned, we have a very unique approach that we're taking in vivo that also allows us to take advantage of the embryonic stage of development of our in vivo model, where we take advantage of a natural curing process where the embryo is naturally and orally consuming the amniotic fluid prior to hatch. We are then able to identify the location of the amniotic fluid and introduce the specific bioactive compound in question, or a combination of different bioactives to look into a synergistic effect. By that, we can specifically target the gastrointestinal tract, and as a result, other tissues, or investigate other tissues or samples that can also react to the specific treatment that is investigated. There is about 70% similarity between the gut genomics of human and chicken, which is a significant advantage. This approach is rapid, it's high throughput, and thus allows us to conduct a very comprehensive analysis of how the questioned bioactive or combination of bioactives is affecting the tissue in question in vivo. To provide additional context to what we are discussing today, I just want to highlight the work that we did with steel beans. Steel beans are polyphenols that are found in grapes in high concentrations. And I'm sure that many of you are familiar with the concept of the French paradox that was presented during the 1990s, where the claim was that despite the consumption of high fat diet, the prevalence of cardiovascular disease in populations that are regularly consuming red wine is relatively low. And the immediate suspects were, of course, polyphenols, or the specific steel beans that are found in grapes or in red wine, specifically resveratrol and steel beans. What we asked ourselves initially was that, what is the link to intestinal function and microbiome? And through this model, we're able to demonstrate that by introducing the purified compounds, again, of the two bioactives that I've mentioned, we're able to show positive effects on intestinal functionality, morphology, specifically of the brush border membrane, again, the digestive and absorptive surface in the small intestine, and also the positive effect on the microbial composition and their function. Specifically, we're able to show that certain bacteria are able to break down these bioactives into their metabolites that are associated with the health benefits that we're after. This resulted in a patent that is listed here, Grape Steel Beans for Improved Gut Function and Health, and the associated publication is listed here on the bottom right. So at this point, and based on this research, we were then interested to gain a deeper understanding as we were shifting from the effect of these specific bioactives on what grape pumice as a source can do. And with that, I would like to invite Melissa to continue.
All right, thank you so much. My name is Melissa Wang. I am in the third year of my PhD degree here, and I'll be going through a study that we recently completed on looking at grape pumice, where we were able to highlight that grape pumice indeed has an anti-inflammatory potential, specifically by normalizing some phenotypes that we induced in our model. So I wanted to reiterate that grape pumice is a significant source of phenolic compounds or key bioactives. It is reported that grape pumice can retain nearly 70% of what is originally found in a fresh grape before juicing. And these bioactives or phenolic compounds are well studied, both in their purified isolated forms as well as within foods, specifically to reduce inflammation, oxidative stress, and so on. So the material that we used came from the Concord grape variety. This is a variety grown heavily in New York State. And we measured the phenolic profile or the phenolic composition of this material and can show that there is a diverse profile. There are different types of phenolic compounds as well as a high amount. And we have to thank Ian J. Gallo for helping us do this. And so with this material in our hands, we wanted to challenge it to see if it could truly reverse intestinal inflammation phenotypes in ovo. And the way we did this was to use our intraamniotic administration model as discussed earlier. And generally it looks like this, where we take advantage of the process, inject our test substance, and then collect tissue on day of hatch to then assess health impact of that test substance that we injected. For this study, we adapted it a little bit to add a second, hence the double intraamniotic administration. And we did this because we wanted to first induce inflammation with DSS, which I will describe in a little bit, and then intervene with grape pumice. So what exactly is intestinal inflammation to begin with? This is actually, it's a normal bodily process to interact with the external world. In cases where this response becomes abnormal, this can cause low-grade inflammation and even range to more acute and severe conditions. One probably that is well known is IBD. And intestinal inflammation it can be summed up by three systems not functioning in their normal way. The first being the barrier or the intestinal lining, the second being the microbiota, which then results in dysbiosis, and also the inflammatory system within the gut that then skews towards pro-inflammatory signaling. So DSS, as I alluded to earlier, is an acronym for dextran sulfate sodium. This chemical is a very well-studied inducer of inflammation within the colon. So it's well reported to mimic ulcerative colitis, a type of IBD in humans. Commonly used in mice at the moment, but it's becoming a more prominent model within chickens, which is what we were using here. Dextran sulfate sodium, or DSS, is able to induce these three dysfunctions within the gut. For the sake of this presentation, I'll be focusing on these two readouts, which is what we revolved this manuscript off of. So the first thing that I wanted to assess was barrier function. I did this by looking at the permeability of the gut. So in a normal gut system, which is the yellow kind of pictograph on the left here, the enterocytes, or the cells that line the intestine, are held together in a way that would not allow certain molecules to pass through into the bloodstream. But in the case of an intestine that is unhealthy or has lost its integrity, has increased permeability, or is quote unquote leaky, it will allow molecules such as PHIT-C, in this case, to pass into the bloodstream. PHIT-C is unique in that it's a specific size, first of all, it's 4 kilodalton, it's also fluorescent. So we can measure the fluorescence of the blood to see how leaky the tissue is. Because of the very novel approach that we were taking in this study, we were only able to dedicate a low number of biological reps to this assay. But with that being said, we were still able to see pretty interesting results where grape pumice, groups that received grape pumice, including those that were first challenged with DSS, had lower fluorescence in their blood, meaning that the gut was less permeable or more integral. This gave us reason to move further and to look at the molecular scale of the regulation of the tissue which kind of culminates on this tight junction complex pictured here. This is a group of proteins that regulate the selective permeability of the intestinal lining. We looked at two key structural proteins that sit right in between the enterocytes. And consistent with previous results, we saw that DSS deregulated or decreased the expression of these tight junctions, and grape pumice, as an intervention, was able to normalize. In other words, the expression level is statistically insignificantly different from the controls. We then dug even further and wanted to look at the inflammatory signaling pathways that feed into these tight junctions to see, okay, is grape pumice causing a change at this level that would then impact the tight junctions themselves? And this is the key pathway that we wanted to test. We saw, again, a normalizing effect by grape pumice from the changes that DSS caused. So in summary, just briefly, this study was able to kind of establish a really unique adaptation of our model where we can first challenge the chicks and then intervene with something that we're most interested in. The second was that we're actually able to see molecular changes of interest for grape pumice, which gives us reason to pay more attention to it in terms of its nutritional benefit. And with that, we actually were able to build off of this study and look at a peripheral tissue, specifically a skeletal muscle. So I'll hand it off to Elad.
So as Melissa prefaced, I'm going to talk to you guys today a little bit about our research into the double injection model, specifically evaluating grape pumice in connection to skeletal muscle. So why do we look at skeletal muscle? Well, beyond being highly predictive of longevity as a result of its crucial role in systemic health, the coincidence of skeletal muscle with irritable bowel disease is approximately 50%. That makes it one of the highest or most common comorbidities of intestinal disease. And even further, the loss of muscle increases the morbidity of these diseases and reduces quality of life. So this connection mainly exists because the inflamed intestine changes systemic metabolic milieu. That means leakiness at the level of the gut can promote systemic inflammation, which in turn in muscle decreases or increases rates of catabolism, that is the breakdown of muscle, and nutrient malabsorption associated with intestinal dysfunction reduces systemic nutrient availability, which reduces anabolism. And therefore, the synergism of these two effects, that is less building up, less anabolism, and more breaking down, more catabolism, results in muscle loss, also called atrophy. Now, at the same time, polyphenols in of themselves directly can reduce rates of muscle catabolism by interacting with catabolic signaling. But also in cases of intestinal inflammation, it has polyphenols in grape pumice specifically have the potential to indirectly attenuate inflammatory bowel associated atrophy as a result of normalizing intestinal homeostasis. So therefore, we asked whether, in addition to improving the health of the intestines, whether grape pumice would also attenuate potential comorbid effects in muscle. The first thing we looked at was muscle cell, also termed myofiber morphology. Specifically, we looked at the diameter of muscle cells, as this is a reflection of the growth dynamics of the tissue throughout and during treatment. We found that DSS significantly reduced myofiber diameter on average by 35%, and this is suggestive of a atrophic phenotype, that is, these muscle cells lost volume. And notably, grape pumice, concurrent administration of grape pumice completely prevented this effect, suggesting a muscle protective or anti-atrophic effect. Notably, these effects coincided with those of the intestines, that is, DSS dysregulated and grape pumice normalized. And therefore, we speculate that the main driver of this is at the level of the intestines. In other words, grape pumice is indirectly exerting bioactive effects by normalizing intestinal health and and by extension, modifying those systemic signals. We also looked into a potential direct avenue of bioactivity, specifically the expression of MyoD and myogenin. These genes are very crucial to early life growth trajectories, and at the same time, in vitro work has showed us that they can be modulated and promoted by many phenolic compounds found in grape pumice, such as anthocyanins, flavonoids, etc. And again, in line with changes in myofiber diameter, we saw that DSS blunted the expression of these two transcription factors, and as a result, potentially contributed to atrophy. At the same time, grape pumice reversed this effect even to above baseline, and in some cases, although not statistically significantly. Therefore, we hypothesized that in addition to indirectly benefiting muscle through normalizing intestinal physiology, grape pumice may directly interact with muscle, bolstering those anti-atrophic effects, essentially. So altogether, in this preliminary study, we found various potential direct and indirect avenues of grape pumice bioactivity in skeletal muscle, particularly in cases of intestinal inflammation. Ultimately, further research is certainly merited in these areas, as at the end of the day, the study was preliminary, and the causality, weight, and stability of these effects over time should be assessed. And more broadly, this study just exhibits the potential myriad of uses for upcycled ingredients for various different health effects. And so on that note, I'm going to hand it over to Peter Gracie, who's going to tell you a little bit about some of those other potential uses.
Thank you, Elliot. Yes, I'm Peter Gracie. I'm a first-year PhD student, and I'm here to discuss some of the other potential options that the Tako lab has looked at in terms of ingredients and bridging those ingredients from research to industry. So I'm going to talk through in my section of the presentation 4 recent research papers published by the Tako lab. And I just want to point out there will be QR codes on the slides that you can scan and get more information about articles that I will be discussing. So to look at another major fruit that's used for drinking is apples. So apples can go to cider, they can go to juices, they can go to purees. And the biggest apple producers are China, Europe, and the US. With the US producing 4.9 million tons of apples in the year 24 to 25. And New York State, where we are situated right now with Cornell University, was the second largest producer of those apples. Now, according to the USDA, approximately a third of apples produced go to processing. And that processing, like I say, can be cider, can be juice, can be purees. And if 25% of that fruit is left over after that processing, then over 400,000 tons of apple pomace can be produced every year in the US alone. So we felt that we had to check how we can use this upcycled ingredient in our model. So we used the actual product, so apple juice, and the two leftover ingredients potentially is apple pomace and apple pulp. And from this research, where we use the ANOVA model that has already been discussed by previous speakers, we found that apple pomace delivered the most beneficial effect to the model, noting that gut morphology was one of the more beneficial effects. And with this, we felt like we had to take that next steps instead. Those next steps to transfer the ANOVA model into a real-world solution, because we can see that upcycling ingredients can affect 3 of the UN Sustainable Development Goals. 2.4, aiming for sustainable food production. Goal 3, ensuring healthy lives. The previous research has already demonstrated that there is the potential for increasing health effects. And 12.3 aims to reduce food loss, and this can directly affect that. So how can we as a lab translate this research and give it to the food industry to hopefully increase the amount of use of these products? Now, what we first conducted was a narrative review on the use of apple pomace and grape pomace in meat products. This has already been done throughout the research, And what we've been able to find is that apple pomace in meat mediums like burgers and sausages and some types of pate increased the amount of fiber and had a minimal effect on minimal sensory effect when added in the correct proportions. And then the benefits of grape pomace in those same mediums, it was found that they could potentially extend shelf life due to the polyphenols present acting as antioxidants and reducing the amount of rancidity in those meat products. And I feel this is how we can get on board meat producers. So because an extension of shelf life means an extension of profits. So, well, we also wanted to conduct our own research in this space. So we identified the problem, we contacted cideries in the local area, and I tried to analyze which challenges would they face trying to incorporate apple pomace into a new upcycled shoot-off. So we wanted to create a solution. So we developed our own apple pomace using apples that would generally be used in cider production, and then trying to ensure that it can be used. So we freeze-dried the apple pomace that was left over, ground it to a fine powder to ensure that it would look like an ingredient familiar to the food industry. And then we tested this ingredient in a familiar medium like meatballs. And so we conducted, this allowed for subjective and objective testing of the apple pomace in this medium. So what we found in this study was that we were able to increase fiber, which is absolutely vital due to Western society not getting enough fiber in their diet. But also we conducted a sensory study with over 100 participants. And these participants found no significant differences between our control meatball, our 10% apple pomace inclusion, and our 20% apple inclusion within the meatball. And these were across 5 different characteristics of appearance, aroma, flavor, mouthfeel, and overall liking of the product that we presented them with. And this is important because a non-significant result actually means that it could be accepted by consumers if this ingredient was used more consistently. But how do we take that next step? How do we find even more things to use potentially in our model or potentially to bridge to the food industry? So our lab conducted a systematic review looking at, and we found that 14 different byproducts in the industry were used. And then this was used across 4 in vivo models. And surprise, surprise, if you increase the amount of fruit or vegetables that you put into an in vivo study, you find benefits. You can decrease the amount of glucose in the blood, to decrease the amount of cholesterol, and decrease the amount of lipid accumulation in the liver. And these were just some of the beneficial effects that we found when we done this systematic review. So what I want to leave you with is that we can use research to show the health benefits of these byproducts, but we can also bridge the gap between research and the food industry. So with that, I'd like to hand off to Matt, who'll discuss bring it back to full circle.
All right, so before I do that, I saw there might have been a question in the chat from the Upcycled Food Organization. Feel free to jump in.
I think that was a bump by mistake, so keep on rolling. Thanks for checking.
All right, sounds good. So to bring it full circle, as I mentioned earlier, these bioactive compounds are what give fruit their color, and they're most commonly found within the skins. Now, I want to help inspire you guys to become more interested in what these throwaways are comprised of. So I'm going to talk in detail about what bioactive compounds are and what the functional components of these upcycled ingredients are beyond just the fiber. So what is this gold mine we're sitting on? First, I want to kind of highlight what are bioactive compounds. And these are naturally occurring chemicals in foods that have effects beyond basic nutrition. So beyond just basic carbs, fats, and proteins, they have a variety of different health benefits. Now, there's a certain type of bioactive compound that is from plants, and these are what are known as phytochemicals, which influence cellular processes and health. On the right, you can see a chart that goes through the classification of dietary phytochemicals And just to kind of let you know where we've been hanging out on this chart, we've been within the phenolics. So there are many more dietary phytochemicals to explore. And this chart really is just kind of the beginning of exploring the health benefits that live among these chemicals. Now, among the phenolics that we just talked about are the polyphenols, which are a type of phenolic compounds that have multiple hydroxyl groups, which modulate oxidative stress, help with inflammation, and influence different metabolic pathways. So for those of you without a chemistry background, those are the OH groups, which are highly reactive. And I'll get a little bit more into the chemistry here. So the polyphenols that are found primarily within grapes and apples, I want to highlight two of them specifically today that consumers are aware of. Within apples, they're very high in quercetin, and grapes are known for resveratrol. Now, apples being high in quercetin, the consumer is aware of quercetin's health benefits, and we really saw that this became more and more popular at the start of COVID. On the right, you can see some Amazon products that are ordered, thousands of these bottles ordered each month that are just quercetin supplements. And you see the same thing with resveratrol supplements as well, which is another plant-derived phytochemical. But how does Mother Nature do it better than these supplements? So on the right, you can see different forms of quercetin that exist in nature. The top left would be standard quercetin. On the right, you can see isoquercetin, which is basically you take a quercetin molecule and you attach it to a sugar molecule. So it's quercetin holding on to a sugar. And then in the bottom, you can see what's known as rutin, which is quercetin attached to a disaccharide. So a sugar that is comprised of two subunits. Now, the benefit, or I guess the challenge with quercetin is that it has poor solubility. So when you eat, if you were to eat just pure quercetin by itself, it would probably be pretty poorly absorbed because it wouldn't interact with your digestive surface as easily. But it's also highly reactive due to the same reason why it's healthy and has a lot of benefits to your health is the same reason why it can become degraded very quickly when it gets exposed to oxygen and light. So it's pretty metabolically unstable. When we look at quercetin glucoside or isoquercetin, which is quercetin attached to a sugar, the benefit is that if quercetin is kind of attached to sugar, then it can go through your gut and be absorbed through glucose uptake. So think of it as kind of like hitching a ride on sugar, which we have plenty of pathways in our body to transport sugar around. Now, when it comes to rutin or quercetin attached to a disaccharide, the actual sugar down here that you see, this disaccharide is called ramenose, and we don't have the ability to break down ramenose in our body. So what ends up happening, or is what is hypothesized to happen, is unlike isoquercetin, where it's more rapidly absorbed at the beginning of the colon, there's theory that rutin can make it to the more distal parts of your colon, where it then liberates these bioactive compounds, as I mentioned, in the distal part of your colon to kind of activate them. So if you need to deliver benefits to the end of the digestive tract, having these compounds that only can be activated by bacteria in your microbiome is an increasingly interesting way of delivering health benefits. So why does this matter? Well, when we're talking about polyphenols and the health benefits with upcycled foods, a lot of the times we kind of just have to communicate that they're antioxidants, or we say that polyphenols are antioxidants. And really I don't want to say we're shooting ourselves in the foot because antioxidants are well understood, but polyphenols do a lot more than antioxidants. They're not just, and yeah, title of my slide. So they don't reduce the need for your body's recovery systems, they actually strengthen them. And this is because they're mild pro-oxidants. And I like to give the example of kind of like a high intensity interval workout for people who like exercise. It's when you give your body a mild form of stress, whether that be heat or sunlight or exercise, your body has a bunch of different pathways that it upregulates to recover and build back stronger. So when we expose our body to these mild stresses through polyphenols, your body upregulates detox pathways, repair pathways, and actually improves your mitochondrial efficiency. A metaphor or an analogy that I like to give to help people understand this better is that polyphenols upregulate a lot of the same processes that you see when you're fasting. So It's a part of many religions to fast. It's a part of many diets to fast. And there's a good reason. Many of us are chronically digesting food, and your body needs a break sometimes. And it's really healthy to kind of take a break from eating every now and then, as well as polyphenols seem to have a lot of those similar benefits in terms of their health benefits. Which could be a reason why we're seeing stuff like resveratrol becoming more and more popular within the life extension communities. But this is certainly not an endorsement, just an example of kind of where you're seeing marketing go with these new findings that are evolving. And really, we're at the tip of the iceberg when it comes to these findings, where our studies are really trying to hone in on the mechanistic exploration, but I think that this is going to be a constantly evolving field, and we're going to learn more and more about this chart that you see here. And I hope by now in the presentation that you're inspired to take a screenshot of this slide. I'll wait 5 seconds or so just so you have the chance to. I refer back to this all the time, and there's just so much here to continually explore. Now, I mentioned earlier that polyphenols are not just antioxidants, but they do function as antioxidants. And that's just to say that every process in your body releases free radicals and causes oxidative stress. And especially in like health compromised populations, having a little extra antioxidants can really help kind of sponge up some of that extra stress and just keep you healthier. So I've talked about what bioactive compounds are, and now I want to mention briefly the functional components that are in this gold mine, being apple and grape pumice in New York, but I'm sure many others elsewhere. So fiber, we're not eating enough of it. Less than 10% of adults meet the daily recommendation. And if you're not eating enough fiber, it's linked to digestive and metabolic health issues. Now, pumice can be used as a fiber source, as both grape and apple pumice are high in dietary fiber. And what's nice is they both contain a combination of the soluble gel-forming prebiotic fiber and also that insoluble fiber that just helps promote regularity and keep things going. So these upcycled sources can really be used to help close the fiber gap. And let's not forget the antioxidants and the strong function of these antioxidants. If you've ever tasted a meat product that tastes a little off, most of the time that's due to lipid oxidation. So the fats will oxidize if they're exposed to oxygen or light or heat. And by including antioxidants, you can actually slow down that lipid oxidation and extend shelf life in foods that contain fat. And let's not forget about the pectins, which come along with it. So pectins can actually help bind the water and improve the texture of these meat products without adding water activity, and do it while adding antioxidants. So it's really a win-win across the industry. So going from research to impact, we've been fortunate enough to take the patent that was developed through Cornell University and are in the process of spinning it out into a startup called PomacePlus, where we're developing health-enhancing and functional ingredients from upcycled foods. Now, there was a trailblazing market opportunity that has really allowed us to dive in so full steam. As many of you know, the challenges with upcycling is, to get a byproduct back in the industry, it's kind of like the chicken and the egg. What comes first? Is it the demand for the product, or do you get the product ready? But fortunately, we have this opportunity that's really put a fire under our butts to get the product ready, which is that in the poultry industry, people eat a lot of chicken. And when we house chickens that are grown for their meat, they're typically shoulder to shoulder in these environments where they get very little light. And because of these poor housing conditions, they tend to have this chronic low-grade stress and inflammation. Now, the industry has typically responded to this by feeding chickens antibiotic growth promoters, which help reduce the levels of inflammation and ensure that the chickens grow to market size at an efficient rate, consuming less feed. But the problem is when we feed chickens a bunch of antibiotics, we increase the threat of antibiotic resistance for human health. And due to rising public health concerns surrounding this, they're being phased out across the industry. However, through our research, we have demonstrated that grape pumice could actually deliver a similar benefit to antibiotic growth promoters naturally by reducing the gut inflammation of the birds and improving their overall gut health. So really an opportunity to upcycle a ton of this ingredient and ensure that we have a steady supply chain for this. So now beyond the animal side of this, we know there's a ton of benefits for humans consuming these as well. So we've been working to develop a robust supply chain, and we're even working on a number of food applications ourselves. We're also pursuing B2B ingredient sales. So if any of you are interested in getting your hands on some of these ingredients, please don't hesitate to reach out. And with that, let's work together. One challenge that we all have as upcyclers is receiving products that come from food processes that have typically been treated as waste. So when you go to a place that is producing juice, let's say, and they've been throwing out their pomace for years, a lot of the times the way that they throw it out is they put it through a chute that they don't sanitize. So if you're receiving a material that hasn't been sanitized and you need to sell it in a food grade product, then you need to pasteurize it. And the problem with that is you break down a lot of those compounds. So I'm sure many of the challenges that we all share are related to how do we ensure that this ingredient that we're receiving, we can actually use and actually work with. The next would be formulation challenges. So when it comes to upcycling fibrous ingredients, there's challenges surrounding inconsistencies in the product format. They have differing levels of fiber. They also have differing levels of composition, differing solubility. So challenges surrounding formulation is another area that we're happy to connect and be a resource. And with that, I'd like to pass it off to Elad, who's going to wrap it up and conclude our session.
Thank you, Matt. So as Matt suggested, I'm going to make some concluding remarks and suggest some of the next steps that we can take. So as was demonstrated, to advance the upcycling of fruit skins and related byproducts into evidence-based health solutions, several key research priorities must be addressed. Starting with mechanistic elucidation, greater clarity is required regarding the molecular and physiological mechanisms through which bioactive compounds influence gut microbiota, host metabolic pathways, and immune function. Then compositional characterization, systematic profiling and standardization of phytochemicals, fibers, and secondary metabolites across fruit varieties. Processing methods and storage conditions are necessary to ensure reproducibility and scalability. Processing innovations, development of optimized, sustainable, and cost-effective processing technologies is needed to preserve bioactivity, ensure safety, and maintain functional integrity during upcycling. Translational validation, controlled in vivo and human intervention studies are essential to establish efficacy, define dose-response relationships, and identify population-specific health benefits. System-level integration, application of multi-omics platforms combined with computational modeling and AI machine learning approaches will facilitate a systems-level understanding of interactions between dietary compounds, host physiology, and the microbiome. And finally, implementation frameworks, interdisciplinary research spanning nutrition science, food technology, economics, and policy is required to evaluate feasibility, consumer acceptance, and regulatory considerations within circular bioeconomy model. In summary, advancing this field will require coordinated efforts across mechanistic, translational, technological, and policy domains. Addressing these research needs will enable the development of scientifically validated, scalable strategies to transform fruit byproducts into sustainable solutions for human and planetary health. And with that, I would like to thank you for your attention. We'll be more than happy to answer any questions that you might have.
Well, thank you, Elad. That was quite the presentation. It's a lot to digest. I was really happy to hear an accent from Northern Ireland as well. Hello, Peter.
Hello.
I am officially half Northern Irish. My mother's from Antrim, so
yeah. I noticed your clattering. It's lovely.
So I don't know who to address this to, Elad. So perhaps you can help me. The in ovo model. For the because we've got quite a diverse audience. How similar is a chick or chicken microbiome to that of a human, or how replicable is the in ovo model versus what we hope to see in human health? Because obviously you're using that as a model ultimately to be able to extrapolate that to humans, but you can't inject humans. But how do you assess that? How do you determine whether something can be extrapolated from this animal model to humans?
Right. Thank you, Lara. This is an excellent question. So with the chicken in general, as part of my research, I was able to establish its relevance to investigate and explore how diet is affecting nutrient bioavailability, specifically working with iron and zinc. This research started with specifically assessing how biofortified staple food crops is actually helping to improve the bioavailability of certain nutrients, again, specifically iron and zinc, to improve their nutrition. So as you probably know, iron and zinc are the number one and number two global deficiencies. 30% of the global population is affected by iron deficiency, and approximately 20% of the global population from zinc deficiency. So we were working with plant breeders to basically test the hypothesis that biofortification, meaning the using of conventional and non-conventional plant breeding to increase the relative abundance of iron and zinc in a specific staple food crop that is relevant to a specific target population, can potentially improve their nutrition. Specifically with iron, to improve basically its bioavailability, and by that to improve the production of hemoglobin. And by that to, of course, reduce the risk of iron deficiency anemia. So this work that I established about 15 years ago basically set the tone or validated that we can use the chicken as a model in this context of human nutrition. Further on, as I decided to basically take advantage of the embryonic development, as you mentioned, other aspects emerged. For example, the microbiome. So great question. This is actually something that we addressed as well, as we were able to basically demonstrate that there is a significant similarity between the human and chicken microbiome. Other factors that we looked into are more molecular. For example, we looked into how similar are the sequences of key proteins that are associated with iron and zinc nutrition. So for example, with iron specifically, the major iron transporter that is located on the brush border membrane, again, the digestive and absorptive surface in the small intestine, is DMT1. Other example is ferroportin, which is located on the basolateral side of the cell. And other zinc transporter, again, the homology, the gene sequences between chicken and human are significantly high. It's anywhere between 85 and 90%. So no animal model, no in vivo model is going to be human, obviously. But what we do is to use a very wide spectrum of different biomarkers, anywhere from the microbiome or secondary metabolites, or a very wide spectrum of different proteins and their expression, to morphometric and other aspects that can really provide us in vivo a really comprehensive understanding of what is the effect of whatever we're testing. In this case, what we highlighted were these bioactives.
This is slightly tangential, Elad, but nevertheless related. I'm an immunologist by training, and when I think of an immunologist that then became a cosmetic scientist and then got into food. But when I think about the gut microbiome, I also think about the impact on our immune system. So the downstream sort of impact on other messengers, and in particular, the role of anti-inflammatory or antioxidant materials like polyphenols. Is that, and given that you are doing it in a chicken molecule, and forgive me if this is silly, but is there a sort of prophylactic way to prevent chickens against avian flu potentially, and therefore disrupt our supply chain positively because of the downstream impact that it's having on what's happening with avian flu is sort of challenging our worldview, our dogma when it comes to transference between one species and another. Can we actually disrupt that by introducing concentrated grape pomace into their diet, maybe, and change that trajectory?
Absolutely. Thank you for your question. Yes, we still need to work on that, but absolutely, because with the current information that we're able to collect so far, and one study that we did not include in our overview today is a study that, again, we recently published about 2 months ago, where we actually induced coccidiosis, which is a very, very severe condition in chicken. If I had to choose something that has similarity to a human condition, so it would be Crohn's disease, IBD, IBS. And we were able to show that dietary grape pomace at very, very small amounts, so it was anywhere between 0.5% to 0.75%, was actually able to significantly reduce the lesions that are caused because of this condition. So recently there was a call by USDA NIFA for proposals to basically tackle avian flu and what can be done in that regard. And absolutely, if we are seeing some positive effects, again, in the context of other severe circumstances, coccidiosis in this case, we are very much interested to learn how it is affecting or creating better immunity that can perhaps be more prepared for avian flu. Avian flu is a little bit different because we're talking about other circumstances. This is, coccidiosis is intestinal versus, upper respiratory conditions or circumstances that are caused because of avian flu. So we need to think of how to address that. But our perspective, similar to what Matt was highlighting, is that can we include grape pomace, for example, in the diet? In this case, it's chicken, to basically create conditions that will support their gut microbiome, will better support their immunity, and by that to significantly reduce their basically sensitivity to disease, more specifically to even completely, hopefully, eliminate the use of antibiotics in their feed, which can then negatively affect us, the consumers.
Well, antibiotics are at some stage going to run their course, aren't they?
Yes.
If we keep using them, willy-nilly, so we do need to be looking for alternative prophylactic therapies, right?
Specifically with antibiotics, just to add to your point, because it is important, I want to make the point that antibiotics are still used in certain circumstances in North America. In other places like the EU, in Europe, in Brazil, in China, it's no longer in use because they made that shift, again, anywhere between 2 to 5 years ago. So we're a little bit behind, but there is an urgent need to basically find holistic, more natural alternatives to the antibiotics that is currently used in poultry feed and actually other production animals.
It's unfortunate that we've had to have a major disaster where thousands and thousands of chickens were culled for the opinion to change on how we might treat chickens and animal welfare in general. I wanted to ask a question, and it might be to Matt actually, about the use of skins, because I've been having a lot of food waste discussion recently because I'm involved in a food waste prize with X Prize, and we've been talking about, is the purpose of all our lives to reduce food waste per se, or is it to create more food? I mean, I come from a place where I want more people to have food, but I do think ultimately the goal has to be, as a collective, to reduce food waste because of its impact on the planet, and just because it's a dumb problem to have in the first place. In your investigations, have you been looking at alternative uses of the grape pomace waste, and in particular the skins, perhaps via a non-edible route?
You're asking uses outside of food?
Yeah.
I know that you come from the cosmetic world. I think I heard you say
Yes.
there has been interest that I'm sure Elad could speak to, of using this in cosmetics.
Well, there is a brand called Cordelie that actually already, and it's linked to a vineyard in France. It's a French brand, and they already use antioxidants from grape skin in that brand. I was thinking more about other uses that perhaps don't already exist, like bioplastics, fuel generation, novel textiles. Have you guys considered that as an alternative use and potential revenue stream? Because I noticed that you're looking, and maybe that's Elad's question, I don't know. I know that you're looking for things that you think have potentially the biggest business potential, I think, right?
Yeah, and I think it comes down to, like, once we're separating these pumices into their components, that perhaps the stems have a use in textile and the seeds have a use in their oils. But I think for now, our main focus is on the animal feed application and the human functional health ingredient.
Okay, great. Thank you, Matt.
Yeah.
I think that we're going to end there for now, end this session at. Thank you very much to all of you. Extremely high caliber presentation. You're making a significant contribution to the upcycled world, and we appreciate all the work that you do. But we're now going to move on to Kay. I think, is she in the room with you?
Yes, I'm ready. And actually, answer to your question, last question, Lara. My research is actually related to the non-food application
Excellent.
of the waste,
It's like
especially biomaterial.
It's like I planned it that way.
Yeah.
It's like I planned it that way.
I didn't want to interrupt.
No, that's totally okay.
That's why.
We're delighted to have you, Kay, and thank you so much for joining our session. And
Sure.
the Tako Lab have certainly raised the bar in terms of science and technology research into upcycling and upcycle food, and I'm sure you're going to continue. So over to you, Kay. Thank you so much.
For sure. Let me share my screen. Okay. Alrighty. Can everybody see my screen?
Yes, you just need to put it. That's it. That's excellent. Great.
Oh, that's it. Okay.
Yeah.
You're seeing the full presentation mode?
We're seeing the full presentation
okay.
mode. Yeah.
And you're hearing me clearly.
Hearing you clearly.
Alrighty, yeah. Thank you so much, Lara. Thank you so much, Lara and Amanda, for the invitation. And I feel very excited and honored to, present about one of my research projects in front of the Upcycled Food Foundation, where so many people are so passionate about, upcycling of the food waste and make our world to be more sustainable and a better, world for human to live. So with no further ado, my presentation is about innovative and translational research in converting food waste and byproducts into non-foods, which is bioplastics. All right, so a little bit about myself and my research team. My name is Kay Wang. I recently joined Cornell Food Science Department as assistant research professor, so just 1 year in. And my research program focused on precision fermentation, on developing niche ingredients for food and bioproducts from low value or waste resources, with two major focus. The first focus is to elucidate the fundamental understanding, especially on the bioreaction perspective and cellular metabolism, how to improve the yield of a certain metabolite for high-value bioproducts. And secondly, with the foundational knowledge we learned to develop bioprocesses for an efficient, tangible, and scalable solutions of our food waste. And this is a picture demonstrating my current research group that's been taken at Geneva, upstate New York, in the summer of this year. All right, so I'm now going to demonstrate why the reason we valorize the waste. We are fortunate to live in the 21st century, where the science and technology have made our lives so convenient, right? But at the same time, we're also facing lots of challenges that our previous generations have probably never really encountered. For instance, the global population will increase by 26% in the 21st century. And during this time, the demand for food will almost double. And don't forget, at the same time, people are pursuing healthy and sustainable diet and care more about not only the safety and quality of the foods we eat, but also the environmental impact and animal welfare that's embedded in the processes where the foods are processed, right? So it comes to the question that how do we support humanity and the planet coming into the 21st century? So if we look at the global substance flow as the full picture, as summarized here, let me put the pointer here. So this is actually a study conducted by the World Wildlife Foundation in the year of 2017 that is about global substance flow by the dry matter. So they actually analyzed how much dry mass of all the bioresources from the land use for example, pasture land, for arable lands, and also towards the primary productions of all kinds of different crops, towards the processing facilities of producing, like oils, biofuels, and also towards the production of livestock for meat. There are actually lots of inefficiencies that happened in our agriculture and food systems. For instance, for every 4.7 million tons of the food that's being served to our table, there are around 500 million tons of the resources that actually goes into the waste and never being used by the humans, right? So this is a tenfold, right, difference between the waste and actually the food. So there's definitely a huge potential to repurpose those waste side streams into something we could actually use, right? So then one may ask, given such massive quantities of the wasted bioresources, what are the options that that generated in our daily life and we could actually reuse and recycle, right? So there are various types of the bioresources that's actually in throughout our food supply chain. So sorry, let me actually hide the floating panel. Good. From the upstream side, where the crops are produced, there are agricultural waste that's been generated from the crop fields, farms, vineyards, and orchards that are often woody and fibrous. And for the downstream, where those harvested crops are, for the processed in the different facilities for food, right? There are all kinds of processing waste and byproducts. For example, we, as New York State, we are big in apple and grape production, so we have lots of those fruit pomace, also as Elad's research on, right? We have lots of fruit pomace from those beverage and juice processing facilities. We're also a big producer of the dairy, so we have massive quantities of those permeates which are rich in lactose, but often regarded as low value or even regarded as the wastewater. So for the downstream, where those foods are packed and distributed into the consumer-facing business, we have those different mixture of the food waste, usually food scraps from the local grocery stores and dining commons, and also even the kitchen waste from our own households. So given all the options of the bioresources, my research wanted to address a question, how our research could navigate biotechnology to valorize those different types of the food waste and without disturbing the current settings of our food supply chain, and also could enhance the circular economy and promote the sustainability of our agriculture and food systems. So with that, the aim, the motivation of our research team is to foster a world of zero food loss and waste through harnessing the power of microbes. And this could be achieved through precision fermentation and usually through lots of different types of the microbial isolates to convert those agri-food bioresources and waste substance into value-added bioproducts. And biomaterial, especially the biodegradable plastics, is one of the high-value bioproducts we could actually produce from the waste material. So now diving into the bioplastics, why we care about bioplastics, right? So the inventors of the petrochemical plastics like a century ago would never foreseen the huge plastic waste problems that our generation is faced with, right? So according to a study that's conducted in 2019, there are over 353 metric tons of plastic waste that were generated annually. And in all of those plastic waste, there are over 50% ended up in the landfills, and only 9% were actually recycled or reused, right? And if you think about the severe environmental pollution or the health concerns that derived from the plastic waste, we heard a lot about microplastics, right? There are all kinds of news about the microplastics. And microplastics is actually the plastics molecules with a particle size less than 5 millimeter. And there are primary microplastics that are purposely made so small for the cosmetics and pharmaceuticals. And there are also secondary microplastics, which are the smaller molecules that's been broken down from with the physical and mechanical, forces on the plastic waste. And those microplastics can even break down more into nano level with nanoplastics, which is usually invisible for us to see, but they could penetrate the cell membrane easily and could have a severe impact on our human organs. So you probably have heard those stories, right, about those microplastics being detected in marine, freshwater, wastewater treatment plants, or even our drinking water supplies. And we are concerned, as a group, we're concerned about the health risks, but in our society have not understand the health risks with the microplastics so far. So there is definitely an urgent need to replace the conventional plastics, and there are actually lots of global effort to do so. For instance, the United Nations has set a goal to reduce the plastic pollution by 80% by the year of 2040. So not so far away, right? And the Food and Agriculture Organization also recommends bioplastics as sustainable alternatives. However, just like what has shown in this poster, right? To reduce or put a stop on the plastic waste or plastic pollution, it's like turning off the tap of a running water, right? Because they are so massive in quantities. And because U.S. is as one of the largest producer of plastic waste in the world, there are lots of actions and also programs has already implemented the strategies to reduce single-use plastic pollutions by federal and state level agencies. So, yeah, it is definitely good to reduce and replace conventional plastics. But what are the options of the bioplastics that we can actually look at as sustainable alternatives, right? So this poster actually demonstrates the different options of the bioplastics, and they are usually categorized into three categories. One is bio-based, meaning they are derived from renewable bioresources. And another is fossil-based, meaning that they are derived from the non-renewable fossil fuels. And of course, there are some that can be derived either from renewable or non-renewable bioresources. So among all these options of the bioplastics, the PHA and the starch cellulose stands out because they're both bio-based, meaning that they're derived from renewable resources, and they're also biodegradable as in all kinds of natural environment, including marine environment, freshwater, soil, and house composting, and also industrial facilities to treat solid waste, such as landfills, anaerobic digesters, and industrial composting. So what is PHA? PHA stands for polyhydroxy alkanoates. It is a naturally occurring linear chain polyesters that's been stored in cell cytoplasm as energy reserves. They have superior thermoplastic properties, and they're non-toxic to the environment. At the same time, they can be 100% biodegradable. So this picture demonstrating a specific microbial isolate that could produce and accumulate PHA granular, which are the white spheres within the cells. And they're usually triggered by certain environmental conditions, such as nutrient imbalance or growth stress. And as I mentioned, PHA is a linear chain polyesters. So they have monomers of the 3 hydroxy fatty acids, and those different monomers are linked through the ester bond that could facilitate a fast degradation by the microbes from the environment. That's why they are biodegradable. And PHA is also classified into 2 categories based on the number of carbon atoms of the 3 hydroxy fatty acids monomers. There are short chain PHA, there are also medium chain PHAs. So PHA has been commercialized already, and I believe the current, the major market of PHA is still within Europe. Well, US has some startup companies of the PHA, but it's still a long way to go. As you can see, there are pictures demonstrating the actual applications of the PHA. For instance, it could be used for packaging material like films or plastic bags. It could be used for food service like the plastic bottles or utensils, and also for textile applications. And there's actually an emerging area where the PHA can be applied for biomedical and pharmaceutical applications. For instance, PHA can be used to manufacture soft tissue, hard tissue, and implantable devices. At the same time, it could be also used to fabricate for the drug delivery. So as I mentioned, the global bioplastic market is still relatively small. It's less than 1% of the total plastic production annually. Through total plastic production, I meant also including the conventional petrochemical plastic production. But it is rapidly increased due to, by the demand, also because of people more aware of those, plastic waste pollution and finding alternatives for more sustainable solutions. So it is projected to reach over 7 million tons by the year of 2028. And as you can see from the breakdowns of different bioplastics in the current market, PHA is actually pretty good. It's actually the 3rd largest share of the bioplastic market, which is right next to PLA and PA. So the current bottleneck to preventing the market expansion of PHA is the production cost, or the price of the PHA is still much higher, up to 4 times higher than the conventional plastics. So there has been lots of research effort in order to reduce the production cost and make it more economical for the market commercialization. So now diving into our research on the PHA produced from all kinds of food waste. So one of the research projects I have been involved in is about producing PHA from food waste through precision fermentation. So the goal of these projects is to establish a precision or microbial fermentation process to convert the food waste, especially the organic portion of the food waste, into the biodegradable PHA with a dual benefit of food waste valorization, reduction, at the same time to replace the conventional petrochemical plastics. So in this project, we use a unique microbial isolate. It is a halophilic archaea called Halophilix mediterraneae. It could live in a hypersaline environment, and this hypersaline environment could facilitate an open fermentation without any pasteurization requirement. So it is very suitable as a low-cost bioprocess to convert food waste. And as you can see from the transmission electron microscopic image here, the cells can accumulate PHA as intracellular, like whitish granulars during the cell growth. And the PHA that's being produced by this cell, it is a unique PHA. It is a linear chain, but it is a copolymer of 3-hydroxybutyrate and 3-hydroxyvalerate. The introduction of these 3 HV units actually significantly improve the thermoplastic properties of the PHA, which the PHBV copolymer is also of the high value among the PHA market. So the method of producing PHA by these microbes is usually involving the sugar as the substrate. However, as is demonstrated through the metabolic pathways from sugar to PHA, there are limitations and gaps that we want to address. For instance, there are more steps involved, meaning that the yield and the selectivity of the PHA from the glucose from sugars is still suboptimal. So our idea of using food waste is to not using the sugars from the food waste, but rather think about some nutrients that could be derived from the food waste and at the same time provide a better yield of the PHA. So that's why we're looking into the short chain carboxylic acid, mainly volatile fatty acids, VFAs. And those nutrients can be directly produced from the commercially available anaerobic digesters. And as you can see from the metabolic pathways here, the VFA, converting VFA into PHA actually involves much less steps, which potentially could provide a much higher yield than the sugar substrates. So then we have developed this hypothesis that using the volatile fatty acids, which could be readily available nutrients from the food waste, can at the same time provide a higher yield of the PHA than the glucose. So we test this hypothesis firstly through comparing the synthetic VFA mixture with the glucose as a substrate to cultivate the microbe under the same conditions. And we did find that the yield of the PHA from the VFAs are actually much, much higher than that from the glucose. And with these results, we further analyze using the real-world food waste. So we actually ferment the food waste into the volatile fatty acids and obtain the nutrients through filtration. And then we were able to achieve successful cell growth using the open fermentation from the food waste. And we found that the VFA composition and the loading can also influence the growth and the leverage the PHA yield and the composition, which would influence the quality attributes of the PHA. So with this proof of concept, we then delve into develop an economical and efficient process treating from food waste into PHA. So as you can see from those flow diagram, that firstly, we went to the commercial anaerobic digesters, which treat about 20 tons of food waste per day. And we actually sampled the fermented food waste from the AD facilities, which contains the VFAs as the nutrients. So as you can imagine, right, after sampling, I would usually be covered with this, odors from the food waste. So I would very smelly. And then we further process those fermented food waste slurry through the benchtop microfiltration process to remove the suspended solids or the debris from the food waste to obtain a clear solution which contain the VFA as the main nutrients. We call it as the food waste permeate. And then this permeate was fed into the biofermentation process to cultivate the microbes for the PHA production, and then it goes through a series of downstream processes, including extraction, purification, and drying, and finally yield a fine powder of the PHA. The PHA produced from the food waste has been analyzed in terms of the biomaterial quality, and we found they actually have comparable thermal and mechanical properties with many conventional thermoplastics, such as polyethylene. And in the fermentation process, we have lots of waste streams, especially with the high salinity requirement. We have this spent brine, which could, introduce environmental concerns when discharged to local wastewater, local water bodies or wastewater treatment plants. So we developed a process to treat and recycle the spent brine into the media, and then we were able to also recycle this spent media within our fermentation system, which also yield a consistent productivity and the quality of the PHA. So with demonstrating the feasibility of converting food waste into the bioplastics, we then think about other possible waste streams in the food industry. So in another project, we look into the waste streams or byproduct streams from the cheese making process, such as whey permeate and delactose permeate, which are massive in quantities, but they're still considered as the low cost or even treated as the wastewater. So those waste streams contain lactose as the main carbon source. So in this process, we actually had similar, process development compared against the food waste, except for the pretreatment step where we employ the enzymatic hydrolysis to break down lactose into glucose and galactose, which are the viable sugars for to cultivate the microbe for the PHA production. And the PHA powder that's been produced from those dairy permeate also had similar thermal and mechanical properties compared to the conventional polyethylene. So during our experiment, we actually found very interesting observations that we employed different aeration strategies. And which would yield a different, dissolved oxygen profile within a very small duration, like only 24 hours through 84 hours, which is usually overlooked by the commercial biotechnology. However, in our process, we found those different aeration strategy with different dynamic DO profiles could actually contribute to a significant different profiles of our production in terms of the cell growth, PHA production, and substrate consumption. So we wonder why. How can this dynamic DO that could regulate the bioreaction, and how does it influence to the productivity if we commercialize it? So in order to elucidate the impact of this processing parameter, we also established the mathematical modeling to study the bioreaction fundamentals. So we actually established the kinetic model incorporating bioreaction rates of cell growth, PHA biosynthesis, and substrate consumption with the machine learning approaches to through optimization, we could estimate the kinetic parameters which are not easily achieved through the experimental research. So from the modeling, we were able to estimate the reaction kinetics, which are comparable to the established models that's from the literature. And at the same time, as you can see from those simulation charts, our modeling simulations actually aligned pretty well with experimental results, which suggested that without extensive study, our kinetic modeling could provide a better, prediction of the process. And This mathematical modeling also helps us to better interpret the aeration effects. For instance, the different aeration strategies, which is often overlooked from the industrial biotechnology standpoint, could generate a different profile of the dynamic dissolved oxygen, which could regulate the bioreaction kinetics and then influence the reaction rate, which eventually leads to the different patterns from experimental observation. And this difference of the bioreaction fundamentals could play a key role in terms of the actual production. So with that, we were able to collaborate with a local cheese processing company and establish a pilot scale production systems of PHA from the cheese whey. And we were able to obtain some data and establish a techno-economic model. Our purpose was to investigate the economic feasibility. If we scale it up to a pilot scale, even to a commercial scale, what are the processing parameters that would influence the overall economics of the system? So we first established the system with the 6 essential unit operations from the upstream to the downstream, which eventually yield a PHA fine powder from the dairy whey. Then, based on the current commercially available facilities, we added additional ultrafiltration unit to upcycle the spent enzyme within the system in order to save the cost and also reuse the enzyme. And based on the first 2 scenarios, we also added another evaporation unit to recycle and reuse the water and the spent brine within the system to better improve the system economics. So from the mass balance of these 3 scenarios, we found that the scenario 3, which has the most unit operations to recycle, enzymes and water and spent brine, we were able to reduce significantly the water and salt usage, and we would have much less waste brine discharge compared to the first 2 scenarios. And if you look at the key attributes or the key cost items that will be accounted for the total production cost, including the equipment cost, direct capital cost, and annual operating cost, we found that the additional unit operation that's being incorporated into the 3rd scenario would add to the equipment cost and the direct capital cost, but they would save a lot on the annual operating cost. And annual operating cost is actually the most important cost items of the production because it is a recurring investment throughout the years. So we do want to minimize or at least reduce the AOC, right? So if we break down the AOC for the 3 scenarios, we found there are lots of similarities. For instance, the cost of the raw material, which in this case is the cost of the dairy side streams, is has the most share of the AOC. So then we further analyze the sensitivity of the break-even price, which is the price we want to sell our PHA in order to break even the production cost, right, against the different parameters within the system. And we found that the break-even price of the PHA is actually most sensitive to the lactose price. And comparing against 3 available dairy whey or dairy byproducts from the cheese making process, including lactose powder, whey permeate, and the delactose permeate, we found that the use of delactose permeate, which is often regarded as the wastewater in the dairy processing, could provide the best or the lowest break-even price, which is $4 per kilograms of the PHA. And currently, PHA is sold as about $10 per kilogram. So we can actually make a pretty good business case from this scenario. So now with the findings of our studies, now let's look at what are the things we could improve to address for the future studies. So the cost effectiveness is still a major challenge that could hinder the commercialization or more research of the PHA. And as we found from our previous study, the main expenses are from the carbon source and purification processes. with each representing approximately 40% of the total production cost. So in terms of the future perspectives, how or what areas we could look at in order to, address those challenges? I would think, firstly, finding alternative feedstocks besides food waste or cheese processing byproducts. We could find other cheaper or even better alternative feedstock that could provide a much higher yield of the PHA. And also to investigate on the pretreatment method to detoxify or detoxify of the chemicals that could that are already exist in the feedstock and which could hinder the cell growth for the PHA production. And secondly, we could also look at the producer, which are the microbial isolate. We could enhance its activity for the specific feedstock. We could also engineer our process or the microbes to increase the production efficiency and the product quality. And last but not least, we could also fine-tune our precision fermentation strategies through proper selection and the development of the reactor regimes, and also through the optimization and developing low-cost purification processes. So I'd like to conclude my presentation with acknowledgement of my collaborators and co-authors of those studies, and also the sponsors for this research. And I'd like to thank you all for your attention, and I'd be happy to take any questions.
Excellent. Thank you so much, Kay. I guess the biggest question that I had is, we have to come back to, I think, why we use plastic in the first place, and the reason why we use it and the reason why it's so ubiquitous is because it does a really good job, right?
Yeah.
And frankly, as someone who's developed consumer goods for a long time, there isn't really anything that does as good a job. So if you think about maintaining integrity of a product, and that could be a cosmetic formulation or it could be a food product. Cosmetics is usually there is a safety element because we don't want microbes to get in there, but it's usually primarily quality driven. And when it comes to food, it's more safety driven. I don't think you showed it in your presentation, and if you did, I apologize, I missed it. But how do some of your novel PHA bioplastics stack up against the sort of standard plastic equivalents? Because I think for those of us formulating, the things that we found that are available to us just don't perform as well, and shelf life is always compromised. So how are they stacking up?
Yeah, Lara, it's a very, very good question. And I didn't really address that question because my research was focused on main of the upstream process, where how to engineer the process and microbe to increase the yield of the PHA, right? But I reckon that focusing on improving the quality attributes of the products to benchmark the current available, conventional plastics is of vital importance. And our research team is actually looking into that through, looking at how the process, especially the precision fermentation process, could formulate a better, chemical structure of the PHA, for instance, to having more monomers of the HV units to increase the elasticity of the plastics, and how we could, look at from the material scientist standpoint to really increase the property or the quality of the PHA. So this is a hot spot, and we're actually looking at it right now.
Okay, very good. In terms of feedstock, you mentioned the cheese and dairy, and I see that you're sponsored by the Dairy Council, so that makes total sense. I would have thought that something that was lignocellulosic or cellulosic would have lent itself more naturally to the development of a packaging material like like spent grain, for example, which is pretty voluminous in its availability in the US, because the US, although beer drinking is declining, a significant amount of beer is still being made. Or, for example, peels from fruit that has I'm thinking particularly in terms of banana, and because I worked in pineapples previously, pineapple fibers. I know why you're specifically looking at whey, but as part of your research, you mentioned feedstock. Are there any specific types of food waste that you think you might be looking at next?
Yeah, next actually we're getting a little bit like seed grant from USDA, and that is looking at the fruit pomace, like apple pomace and grape pomace, right, as the feedstock for PHA production. Yeah, so that is actually mostly lignocellulosic composition, and we're seeing about a way to transform those lignocellulosic feedstock into viable nutrients that the microbe could assimilate for the PHA synthesis.
So what we really need is for the Grain Association to sponsor your work to look at the use of spent grain in PHA, is what you're saying, basically.
Yes. Yes.
Okay. Okay.
And I'd be happy to make a connection there.
I am sure. I am sure. Did you cover this? We have a question in the chat from Shumin Chen, who's based in Canada. What's the yield of PHA produced from food waste by do you say haloferax or haloferax?
Haloferax.
Haloferax.
Could be halo as well. Yeah, I think.
I was just thinking of halo.
Yeah.
Halo.
Right. Yeah.
Right?
Yeah.
I assume there's something about the shape of the microbe that kind of gives it a halo. Does the yield yes, so she asked the same question is the yield dependent on the types of food waste that you use?
It is definitely. But since my previous research was focused on the mixture of the food waste, so the yield would depend not only on the food waste type, but also on the loadings and other process parameters. But I would say, generally speaking, it's about like 30% yield from the food waste. So which is still not optimal, but we are looking at how to increase the yield.
In your research, I hope that someone from a packaging manufacturer has come to talk to you. I think do you see that? If they haven't, do you see that in your future? Because I think it only works if we take the packaging industry with us, right?
Yeah, I haven't really talked to any because I think we're still in the early stage, but yeah, I would be happy to make connections to the packaging, to the manufacturers, and see what we can collaborate on.
Okay, so I look forward to seeing the functionality of your novel PHA being tested versus, I mean, PHA as it is right now doesn't perform the same way as PP or PET, right? That's the gold standard. So if I may say this as someone who has worked in trying to source different packaging materials for a lifetime, if there's ever a way to unlock that you have a PHA that performs the same way as a standard PP or as a standard PET, then that's a multi-billion-dollar opportunity. So I
agree.
I would love to see, I look forward to seeing the functional data to show the functionality of your novel PHA versus standard PHA and other forms of plastic. Perhaps you can come and present that to us at our next symposium in June for Upcycled Month in 2026.
Yeah, sure. Yeah.
Okay.
I'll be happy to.
Thank you so much for your time, Kay. And we're going to move on to Viral, your colleague Viral. Is Viral on?
I am here. Hello.
Hello, Viral. Lovely to see you. Thank you very much for joining. I see you've taken the Go Red very seriously there behind you.
Cornell, loud and proud.
Very good. Okay. Viral, over to you.
Thank you so much. And slides should just be popping up. So,
yeah.
Perfect. Thank you so much for having me. Happy to be here with my colleagues today and talking about upcycling, something very near and dear to our hearts. Today, I'll be talking about using food technology to enhance upcycling NPD, and just some case studies from the New York Byproducts that we have here in lovely upstate New York. So I work here at Cornell Agritech. It's the New York State Agricultural Experiment Station, and this is part of the land grant mission of the New York State. And what we do is we work directly with producers of food and consumers of food, and we create new products and we grow the industries around them. So I wanted to show this picture of our Seneca Foods Foundation pilot plant. This is where I've done a lot of my work, and this is where we work with a bunch of different startups to full large companies. And if you ever find yourself in the Finger Lakes, please come on by. I'd love to chat about upcycling or your new products. So we've been talking a lot about food waste, and 30% of calories are wasted. But I like to go a little deeper and talk about the two sides of that problem, where 13% is food loss and 70% is food waste, according to the United Nations. So how we'll define food loss is food that is lost before it hits the consumers. So this is a big opportunity for us for upcycling and creating new products, while food waste, 17%, is those that are lost post-consumer. So this is food that's gone bad, probably has low quality, and consumers reject it. And this is also an opportunity to enhance the usage of food and to reduce that wastage that occurs. So here at Cornell Agritech, I really have the question on how can we use food technology and upcycling to lower both these numbers. So in New York State, we are a big producer of Concord grapes and Greek yogurt. You've probably heard a lot about grapes and yogurt today because they produce grape pomace and acid whey. So grape pomace is the leftover residue from juicing grapes, whether it's from making grape juice or making wine. You have that leftover seed, that skin, that pericarp. And then acid whey, that's the acidic whey portion that's removed when you create Greek yogurt. When you create Greek yogurt, you strain off the acid whey, and it is very acidic, and you get about 2 cups of acid whey for every 1 cup of Greek yogurt. So here in the upstate New York, we produce a lot of these 2 wastes. So today, I'm going to be sharing 4 case studies, 2 on grape pomace, 2 on acid whey, and to kind of showcase new product development. And you can use this for any sort of food waste you might be dealing with. We'll be talking about developing new ingredients, consumer-driven new product development, unlocking line extensions, and then the impact of a clean label. So part 1, Concord grape pomace. Everyone is looking for new colorants, new ingredients. How can we use these wastes to produce new novel ingredients, such as grape pomace powder? So my colleagues Elad and Matt were talking a lot about the benefits of grape pomace. And one of the problems with grape pomace is that it goes bad very quickly. It has a high water content, it has a microbial load, and we want to see how can we dry it to produce this bright red anthocyanin, antioxidant-filled powder. So we use this machine here called a microwave vacuum dryer, which uses a vacuum and microwaves to gently dry the food at a lower temperature. And here, we looked at it against forced air or conventional drying. And I just want to point out here on the x-axis that conventional drying takes about 350 minutes to dry your product to a shelf-stable capacity. But with microwave vacuum drying, we can bring it down in as little as 20 minutes. This is awesome because this allows us to dry massive amounts of pomace. So when you're producing wine or producing juice, you're producing a lot of this pomace, and it needs to be stabilized very quickly. And again, time is money. So by stabilizing our product within 20 minutes, we can produce a product that is fast and economical. But we want to take care of the red color and the anthocyanins. So again, on your left, we see here total phenolic content. This is the anthocyanins, what gives that antioxidant, that bright red color. And we see during forced air drying, we lose about 50% of those anthocyanins to become oxidized. However, with microwave vacuum drying, we actually see an increase in our total anthocyanin. So microwave vacuum drying protects and releases anthocyanins, producing that bright red color. But what can you use it in? So grape pomace can be used in multiple product categories. Here at the top left, we see a chocolate cookie with 0, 10, and 12% grape pomace addition. We see it gets darker over time, but still maintains that flavor. And you get a little bit of that chocolate and berry flavor from the pomace. But we can also create new and exciting products. Down below, we have dried bars using, again, microwave vacuum drying. And these have added proteins from hemp or other seeds. And these produce snack bars utilizing grape pomace as the base. And then to our right, we see here novel structured gels. This uses grape pomace and added protein, which we can use to create protein gels for athletes or consumers who are looking for more protein. And we can create different kinds of gels, one that is free-flowing, more like, say, an applesauce, or a firmer one that is produced using high-pressure processing that uses pressure to structure this gel, kind of like how you would have a cranberry sauce. Now, one of the awesome things we can use is sensory analysis to determine how these products work in the consumer landscape. So penalty analysis can inform about product faults. Here, we have penalty analysis for a pancake and a cookie. Both of these are dry mixes that we developed with added grape pomace flour. So it's an easy-to-use product for consumers, but we want to ensure that the product is, it tastes good. And here we see that even between two baked goods, we can see a difference in what consumers like and perceive as dislikes. So on the x-axis of these graphs, we have percent of consumers, and on the y-axis, we have how much their overall liking decreased. And we can see that unpleasant aftertaste is quite high in pancakes, but not there in cookies. So this shows us that different types of products can very much change how consumers can taste and perceive the flavors. But this can also help us see that an unpleasant aftertaste needs to be modulated of some sort. And much of this comes from grape pomace. So we have this problem where upcycling grape pomace can then lead to off flavors. Here is another way where we can see how processing can affect our faults. Here we have our gels that were produced via heat or high pressure processing. And I'm going to use these two errors to show much too much grape flavor and not enough grape flavor. And you can see by the distance between the points that processing can highly affect how our products are perceived by consumers. In this case, HPP gels are considered to have a less amount of grape flavor, most likely because they are gelled compared to a softer, more mouth-coating puree. So this is showing us that we can use different types of processing to increase consumer appeal of these upcycled foods. But one thing that's very interesting is that consumers are driven by health. So here is a check all that apply from one of our sensory analysis. And we see that high protein, minimally processed, high in antioxidants, these are liked by consumers. And all of these typically come with upcycled foods because, say, grape pomace, it's high in antioxidants, and we can have it minimally processed, and it's high in fiber. So this shows us that consumers like these kinds of products because they believe that it is more healthful for them. A lot of us also talk about how it's great for the environment. Here we have a max difference on this bottom table, and we see sustainability has a negative 12 compared to taste on the other end, which has a 34. So what does this mean? This means that sustainability does not matter that much to consumers, and that taste is more so a factor when it comes to producing these products. So when we as producers and scientists are creating these products, we always have to keep in mind that taste is king. And though we tend to drive sustainability as a way to increase purchase intent, ultimately, it may not be the deciding factor for consumers. They're driven by their own personal health and flavor. So next, we'll be talking about yogurt acid whey. And here is a great example of unlocking a new product line. We already talked about how acid whey is produced. You take milk, make Greek yogurt, and you get money. But you produce this acid whey, and it can go to a low-value output. So what if we produced a secondary product line? You're already creating yogurt in your factory. What if you then mix those yogurt with the acid whey and produced a new novel beverage that can get you more money? And here we see that by adding 35, 40, and 45% acid whey to a yogurt base, we can actually enhance its physical stability and create this beverage. As you see by these green arrows again, we have enhanced stability from our product, from our acid whey product. But you want to know, what does it taste? And we ran a sensory analysis, and we found that up to 35% substitution with acid whey was well liked by consumers, meaning that you can remove up to 35% of your high value, high cost yogurt and substitute it with acid whey to take that byproduct and produce a new novel product. But remember when I talked about food waste versus food loss? We can reduce this waste by extending shelf life. And one of our novel processes I've been talking about is high pressure processing, as you see here. And through high pressure processing, we can actually extend shelf life while maintaining that probiotic content, because it reduces, it increases our stability without using heat. But furthermore, we can effect a structural change, which further enhances the quality of the products. And if a product has a longer shelf life, a higher quality, consumers are less likely to toss it out and thus reduce food waste. And finally, I'm going to talk a little bit about a sports beverage that we created with acid whey. So acid whey has a high amount of electrolytes. As you can see here, a lot of potassium, a lot of sodium, something that you would need when you're running. So we thought, what if we use a novel deodorization technique to remove those off flavors of acid whey, so we can use it beyond just yogurt beverages and use it in new different beverages that have different kinds of flavors. And we found that with 5 minutes of deodorization, we can actually enhance the aroma liking and flavor liking of these beverages. And you can see here we have our different beverages and an increase from 22% to 34% of those who like the beverage. But this gives us a special kind of thing to look at here, in that when you're using acid whey, it has all of those sodium, those potassium that are already in there. We can produce a clean label product. So here we have our product: yogurt acid whey, water, lime juice, sugar, and ginger juice. And we wondered, what if we compare this to another sports recovery beverage? I'll not name what it is, but you can see its ingredients here. And we ran a discrete choice analysis. Can we see, do consumers actually like a clean label product if it's upcycled? And we found that if consumers are just shown the ingredients, there is a positive willingness to pay for these clean label. And that's actually 9%, or 9 cents. So consumers are willing to pay 9 cents more for a clean label product versus unclean label product before tasting. However, once the product is tasted, we see that it becomes negative. And this is because flavor is attributed to that clean label. And we actually see that there is a 22-cent discount. This means that consumers would spend 22 cents less for a clean label product if they do not enjoy the flavor. So as I've been saying for this entire talk, flavor is king. Flavor guides consumer spending. However, if you can use a product like our cookies, which consumers are more likely to enjoy because they are sweet and they're an indulgence, we can add up to 12% grape pomace and not reduce purchase intent. So through those 4 case studies, I hope I gave you just a little thought about developing new ingredients and how we can use consumer insights to drive new product development, unlock line extensions, and see how the impact of a clean label can affect consumer purchase. I want to say thank you again so much for having me, and I'm happy to talk. Lara.
Thank you, Viral. Thank you very much for that. Yes, taste is king, and I noticed the categories that you tried. Are there any categories that you tried that just didn't work at all from a taste perspective? And also texture. I don't think you overtly mentioned texture, but texture is also critical, right?
Texture is very important. Yes, texture we looked at in our yogurt beverage, and that was also a deciding factor. That's why I show how we can extend the quality. We have tried multiple different kinds of products, and we found that those that don't work typically are those that the matrix does not fully stay together. So say a cheese sauce with acid whey can become too acidic and it splits. So understanding how the matrix is controlled and how flavor is modulated is very important.
So what's next for you in terms of product development? What haven't you tried that you really want to try in terms of using upcycled ingredients?
Yeah, I've tried tons of stuff, and we're looking at different vegetable pomaces. We're looking at different waste. I'd love to look more at waste from the meat industry and the fish industry. We have a lot of bones and scales, and how can we use those to either supplement or create new products? And like how we were talking earlier, just creating non-food products, creating packaging, creating supplements, new ways to upcycle and reduce food loss. And better help our planet.
Yeah, I thought when you said you wanted bones and shells, I was thinking you want to make food, but I guess I see that pet food is one of the fastest growing categories just generally, prestige pet food, and we're seeing it growing significantly within the upcycle food category. Is that something that you're also considering?
Oh yes, I love pet food, and just doing sensory analysis with pets, that's a lot of fun to bring them all in. And I definitely think that food waste valorization can play a role there. We already feed food waste to animals for agriculture.
Right.
Why can't we bring that to our furry friends?
Yes, our fur babies. I don't have one, but yeah. So if you had an ask of this group listening to you, Viral, what would that ask be?
I think the ask is really understand what food waste you have, and though it may seem impossible with some things, I'm sure you can find a way to use it. There are tons of different technologies, tons of uses, and if you ever want to give me a call, I'm happy to chat about what we can do with what you got.
Brilliant. Okay, thank you so much, Viral.
Thank
and that
you.
concludes our session from Cornell. Huge thanks to all the Cornell team. You were amazing, and I think really gave us a lot of food for thought this morning. That's not the end of the Upcycled Symposium, though. It's time to transition over to Amanda. Amanda, you're going to introduce our next speaker, right?
I am. While joining you in that resounding applause for Team Cornell. Thank you for championing upcycling. Thank you for all the knowledge you shared today and really pushing this innovation forward. So we look forward to following along with your progress, having you back in the future. Definitely speaker information will be shared. So collaboration to come. And in the spirit of that, excited to bring on our next speaker, welcoming him back to the stage. David Wishnick is co-founder of longtime founding UFA member Nutraberry. So I feel like this is such a great segue from what Viral was just saying of, looking at making the impossible possible. So David, I'll hand it over to you to talk about your upcycling journey and what's new since June.
Thank you so much, Amanda. I appreciate the opportunity. Hopefully everyone can hear me okay.
You're coming through clear.
Great. I appreciate the opportunity again, Amanda. Thanks a lot. And for the UFA, I appreciate the opportunity as well to everybody. We all know the fable that one person's trash is another's gold. I hope to share that fable with you, but through the agricultural byproduct and fibers that usually go to waste lens, and how Nutraberry can create high-value functional ingredients from these undervalued fibers. Our work is supported by the USDA funding and is part of our effort to bring clean label, microbiome enhancing ingredients to market. Global food manufacturers face critical shortages of clean label ingredients, been talked about. Mars has invested $250 million in a sustainability fund to target advanced agriculture, low emission, better for you ingredients, and circular packaging. That's clear. It's a clear market demand signal. Meanwhile, billions of pounds of incredibly nutrient-dense ingredients are wasted. Fruit seeds, almond hulls, chickpea hulls, peanut skins get wasted every year. Why? Because existing processing technologies simply cannot handle these tough, fiber-rich materials effectively. Our breakthrough advanced milling technology transforms these impossible to process fibers into ultra-fine fibers that integrate seamlessly into any food application. Ever dig in yogurt and notice there's no seeds? We started in Washington State, where 95% of the raspberries in the US are grown, and buy from suppliers of seedless puree to Danone, buying their seed slurry, byproducts, and turning them into 3 revenue streams. First, we dry the seed, press it for oil, and there you can see our oil press in the lower right-hand corner. And the fatty acid oil fraction retains the fatty soluble nutrients like vitamin E, but the defatted fiber that you can see coming off the oil press retains the water soluble nutrients, created a 1:9 ratio. Second, we started milling that defatted fiber for exfoliants. But third, and most importantly, we precision micronize the defatted fiber powders for food applications. And the ultrafine fibers solve real formulation problems that have plagued food manufacturers for decades. CPG wants to upcycle and the functionality that we bring to the table, but as already discussed, they'll never compromise texture and taste to do so. Doesn't work. So this isn't milling, this is precision ultrafine micronization that turns waste into profit. And here's the science. In their natural states, many polyphenols are trapped inside the cell wall matrices, essentially bound and inaccessible to the microflora that either are fermented with or in the human microbiome. But when we micronize, we break open those walls. We rupture those walls, making them available. This is what the diagram is meant to reflect. And with our USDA funding research and with WSU and King's College in London, show that 5-micron defatted fiber powders have 34 to 86 more available ellagic acid, which is what polyphenols are, the poly, and of course, ellagitannins is the polyphenol we study with the raspberries, than the control, the stone mill 210 micron. That's a dramatic increase in bioavailability substrate for the human microbiome. And that means greater production of the healthy metabolites in the human microbiome that support gut and metabolic health. So this isn't just about berries, it's a platform. We've grown since then, and we've applied many other substrates like chickpea hulls, and those are pictures of peanut skins. And there's other substrates that we're using, and each byproduct is currently undervalued and can be transformed into microbiome active fiber ingredients. This is just a map of some of the companies that are in our supply chain. Again, we buy from suppliers, that's people that we buy from processors that supply Danone with their seedless puree. Nusicer, for example, is a non-GMO chickpea grower and breeder that maximizes the protein. We buy their hulls from their California Almond Board. For example, is 500 and 700 million pounds of almond hulls being thrown away. Al Barak Date Factory in Dubai, we have fiber from them that they're looking to commercialize. And we've had contact with Hudson Alpha Biotech, Center for Biotechnology in Alabama, which is in the wiregrass region that grows the vast majority of the peanuts in the US. So each ingredient becomes a functional ingredient. The commercial benefits are clear. So our technology is a low-cost, single pass, so it's a continuous process. So we have lower cost, higher quality, no heat, so no damages to these biological matters. For example, working with an algae processor as well. So live cells that they're dealing with. So it's really important to not to have any heat that can ruin these biological actives. Upcycle, of course, it's important to the manufacturers, of course, brand equity, but like you mentioned, the consumer level, it's not the strongest pull, which is why we focus on micronizing was what is eliminating mouthfeel was our original motivation, actually, for utilizing the technology that we do. So we become a platform working across multiple feedstocks. And the advantages of micronizing are not just the mouthfeel and the flavor. It disperses in solubility. It opens up applications that were never available with these feedstocks. The dispersion time is much quicker, so it helps. Utilizing this is not limited by this particular ingredient in that it can disperse evenly very well. Smooth integration. But what might surprise you is that we believe that we can supply the precision fermentation, which was actually the past couple of talks, which aligns well because there's bottlenecks in scaling these up. Nutraberry fits in the broader food innovation ecosystem. Precision fermentation, as we know, is revolutionizing food. Companies are creating everything from novel proteins to next generation sweeteners. But here's the real challenge they face. These ingredients are expensive to produce, often unstable, and can be difficult to incorporate into actual food products at scale. This is where we become a strategic partner. We're not competing with precision fermentation, we're actually the ideal partner. Our ultrafine fiber powder serves as the perfect carrier system. Think of us as a delivery vehicle that makes their innovation actually work in real-world applications. First, our prebiotic fibers create synergistic effects in the fermentation process. Fermentation is the same thing as the microbiome. It's just that you're controlling the microflora. They can actually enhance batch performance and reduce production costs for fermentation companies. Our powders solve dispersion and stability challenges. When you're trying to get a novel protein or bioactive into the beverage or baked goods, our fiber matrix provides the structural foundation that keeps everything stable and evenly distributed. Like we mentioned, flavor and texture are king. Third, and this is the exciting part, what we're seeing, the concentration multiplier. In our USDA trials, we achieved up to 86-fold increase in bioavailability in bioactive compounds in finished products. Imagine what this means for precision fermentation companies that are trying to deliver therapeutic levels of their ingredients. So everyone's talking about precision fermentation as the future of food. We're positioning Nutraberry to be the enabler that makes the future commercialization viable, a reality. We take their expensive, delicate innovations and give them a clean label, cost-effective pathway to market. In essence, we're building the infrastructure that lets the food revolution actually reach consumers' plate and be commercialized. Nutraberry is enabling higher concentrations of healthy actives in shorter times using upcycled ingredients. So we're not competing with fermentation innovators, we're enabling them. We're the structure, nutritional base that helps them achieve success in market. Nutraberry takes what was once wasted and turning it into the foundation for the next generation of food ingredients. By combining upcycled clean label functionality and proving microbiome benefits, we're not just solving waste, we're creating new value across the food innovation chain. Thank you so much.
Thank you, David. Always so good to see where your journey is taking you next from the beginnings in berries. And there's so much potential, I feel like, with what you just mentioned on screen. I know our time is short within your schedule, but do want to open it up for any audience questions. If there is, feel free to use the Q&A feature. And definitely, David, when you're thinking about, current and what's ahead, what are your wish lists of collaborators or kind of folks
if I had I love working internationally, and I would say Al Barak Date Factory was fantastic to speak with at IFT, and that is an aspiration I have personally. I didn't mean to cut anybody off. I'm sorry.
No, absolutely, please. Yeah, and when you think about what is the unlocks, I feel like we've heard a lot today about the challenges within upcycling. It's unlocking the taste, unlocking the flavor, unlocking the scale. And I feel like that is right on time when you think about, this moment of the upcycled movement compared to 5 years ago. What is your perspective on things now and things ahead?
I don't think anything's ever easy that's worthwhile doing. I know it's going to happen. It just makes perfect sense. So yeah, I'm optimistic that it's going to happen sooner than later. I think precision fermentation is the future of upcycling, to be quite honest.
Creating the future of foods right here, right now. We're doing it together. So thank you so much for joining us, and keep us posted on updates. A great segue to an OG, as Laura describes him. I'm going to bring Dr. Lara back here on stage to introduce our final speaker of the day.
Yes. So our final speaker of the day, if you've been with us since the beginning this morning, this is 11 a.m. We're in the final stretch. I'm going to introduce Stephen Grall, who is an engineer, expert in processing animal nutrition, had his own company for 22 years and sold it in 2015, and now works with multiple people advising them on how to design their supply chain systems if they let him. Stephen, you're off camera for some reason. I'm introducing you. Where's he gone? Stephen's been on the line since before 11, and now when I need him to be on the line, he isn't on the line. There he is. Okay. You're on mute, Stephen.
Unmute. Now I got a bunch of screens up here because I've been following these great presentations and just going off on a list of, oh my, what about where are precision fermentation? I got so many, so now I got to close a bunch of screens.
Okay, well, while you're closing a bunch of screens, the caliber and the quality of the presentations today has been so high and so interesting. I'm not surprised you've got multiple tabs open, but you're going to promise me today you're going to have only one tab open when you give this presentation. Stephen, I affectionately refer to as the Willie Nelson of process engineering. If you let him, he will take up the next 3 hours, but he's promised me he's going to succinctly talk about why whey is the OG of the upcycle movement and his experience in working in whey, and I guess some of the challenges and opportunities when it comes to engineering and processing and upcycling whey. Did you manage to get your presentation, Stephen?
Interesting problem, but I'll do it this way.
Okie dokie.
Which screen do you see?
Well, I'll tell you. I can see it's not in presenter mode, but if you put, I see your slide and your notes.
It's in presenter mode on my other screen. Booger.
Okay.
I tried to get all this ahead of time because I'm not this is not, Cornell's got those great systems for doing this stuff.
Yes, Cornell was already set up a profession. While you're figuring that out, I'll give you a few seconds. If you enjoyed what you heard here today, which I very much hope you did, if you're not a member, we would really appreciate your membership. We are already planning for Upcycle Food Month in 2026, and we would like to make this symposium bigger. There are plenty of voices that we haven't heard from that we'd love to hear from in 2026. And we really want this to be your community. This community, this scientific community, has been fostered because we want to support and nourish innovation collaboration within this community. And sometimes it gets lost in bigger networks that are involved in engineering and processing or food science. And I think this should be, if you're working in waste valorization of food, then this should be the place for you. And with that, I'm going to hand over to Stephen, and he's going to run his presentation. We've got a tight end there, Stephen. Okay.
Yep.
So
I'm gonna go.
Okay, off you go, Stephen.
My mission basically is to improve the health and well-being of people on the earth by improving overall production effectiveness, which means making sure that we get our don't waste anything, our resource utilization. I've had success in designing and managing very effective, efficient business case forward food, beverage, and pharma process facilities. And I really appreciate the faith that these people have put in me as I've helped along the way. Now this thing has got to move. They'll just go boom. The original gangster whey, the OG, we all heard about whey from Little Miss Muffet eating her curds and whey. Few of us have eaten it. Cheese production separates casein, protein, fats, and leaving whey behind. That's the sweet whey. Whey is a byproduct of cheese, yellowish liquid with its own protein, sugars, and fats. My father had a career in one of the most effective disposal of this waste stream, that waste stream of cheese production. And I always knew about whey. It was part of being raised on a farm. We fed it to pigs. We picked up whey from the local cheese factory. Oftentimes it was sour and smelled. So Bentel's was our local cheese factory where we actually picked it up. They had this U-shaped tank on a stand outside with a pull chain, which opened a valve to fill the milk cans and the whey haulers. What wasn't picked up to feed the pigs maybe was hauled away to be spread on fields. Eventually, some was spilled. Here is a picture of my dad standing in front of a whey hauling tanker. He started working in this industry in 1965. So in the 60s, the states and local governments saw whey waste as a problem. Foremost Foods of California developed a patent for the dialysis of whey. Dialysis split whey into constituent products. Along with concentration and evaporation technology in the late 1970s and early 80s, the cost of hauling nearly water-like whey dropped as the number of stops whey haulers had to make came down. This is because cheese factories consolidated and grew larger. Foremost became Foremost McKesson, and later in an acquisition by Wisconsin Dairies became Foremost Farms. Most plants obsess over their hero product and ignore the exhaust drips and wastewater. That's where the hidden margin lies. Companies shepherd their brand products, but they give minor focus to the impact their production has on water, as well as land and air. The raw materials and packaging get converted to customer-valued profitable products, and the waste streams are an afterthought to be dealt with as little attention to them as possible. Waste is a yuck factor. However, waste has potential. Waste has mass and energy, with ingenuity can have value. The fastest way for waste, though, is out of sight, out of mind, and that's been the norm. We here in this group are challenging this normal, and we know it's not viable anymore. Our pollution is beyond the capacity of nature to recycle the elements. Sending waste to rivers, land, and sky has a price to be paid, and the debt is mounting and time for it to be paid. The process systems that make way the OG. Growing up with someone in the industry, it was not hard to gather insights and introduction to words like reverse osmosis and dialysis, and having empty bags with labels made lactose and galactose common words. Early on, the market was not for the whey protein, but it was for the sugars. These mildly sweet sugars of lactose and galactose became a go-to for tableting pills. Diluting out the active agent, these excipients compressed well and provided a stable pill shape. Whey was still subject to poor handling at the cheese factories that allowed unchecked fermentation. Fermentation created new compounds with off flavors and reduced the amount of sugar. Whey pickup was done often, several times a day, so that the whey was minimally degraded. Fermentation reduced the sugar yield, and the proteins and fat when dried were often yellow and tasted terrible. The consolidation of factories, refrigeration, membrane processing to concentrate the whey reduced the spoilage and increased the amount of sugar available. This also reduced the off flavors present in early whey protein separations. Research institutions, which you've been hearing about today, made huge strides in the 70s, and then industry followed with larger scale capacity in the 1980s. The development of ultrafiltration membranes allowed the fractionation of the whey proteins for whey concentrate and several whey protein isolates. Further advancement in processes saw microfiltration to separate remaining fats, delipidization, nanofiltration to remove minerals. These innovations reduced cost, improved and broadened the range of products. Interestingly, membranes largely replaced ion exchange, except for those highly selective dialysis techniques needed for precise protein and peptide separation. By the early 2000s, a comment by my dad was, in effect, that the profits for whey products were greater than that for cheese. His statement was a bit more on point. If we could just get rid of the cheese, we could make some real money. The government milk price support kept buying cheese. Whey could carry its own without support. As we entered the 2020s, we now have markets for 30-gram and likely higher protein beverages using ultrafiltration of skim milk, leaving the sugars for the whey industry. In my early post-college days, my first engineering and site management roles were assembling and installing reverse osmosis and ultrafiltration system. I worked building Vermont's whey processing infrastructure in 1984. Suppliers back then like Pasilac, PCI, Damro, and Abcor were common. Early RO and UF drying and bagging technologies were employed. Multi-effect evaporators and various styles of dryers were developed from companies like Nyro, Alfa Laval, Damro, Sheffers, APV, and Filtermat. Process development and efficiencies improvements continued. The pace and variety of techniques have fallen off with the equipment industry consolidation and maybe less basic research investment. The heady times of the 80s and 90s for process installations created market saturation. Automation and knowledge gained by serving this saturated market has provided some continuing efficiencies and incremental improvements. Today, specialty companies like MP&C, Covalis, and Colaris continue with deep technical expertise. The founding process equipment providers have consolidated to broaden their offerings, serve wider markets, and continue to development of components such as pumps, valves, heat exchangers, membranes, etc. These consolidated companies have a worldview and footprint, but just have a few process expertise specialties. You can see here in this chart how many different process techniques are needed in order to get out the various ways and various market streams that whey can be divided into. Whey is the success story of upcycling into more profitable products. It did not happen without subsidies and government requirements for the environment. Like Wisconsin, other states, including Vermont, New York, and California, have had their success stories. University research developed the core science that gave the push industry needed to explore business opportunities and markets to achieve the upcycling success. My dad once said, if a product has a registered trademark on the package, it likely has whey component in it. And as we talked back at the last symposium, Dr. Lara here was saying whey is the OG of upcycling. Now, to talk about the next frontier, the integration that is going to be that next frontier, not every business can enjoy a partnership of government, universities, and process system providers to show that their waste and side streams have ROI. It took 2 decades for whey to prove itself more valuable than cheese, but now the industry of upcycling processes are available and the physics of these understood. Companies can be coached to look at their side streams as a resource instead of a waste. A holistic approach can be viewed by a collaboration of operations managers, engineers, etc., especially along with the financial investors. The diagram shows that the workings inside a company's system boundaries appears quite chaotic, and it is likely chaotic to most, if not all, the employees. This is how it is when I joined, it is as I work here, and the is that is all that I really know. The history is never discussed. We tend to solve problems one at a time without thinking through the system in its entirety and how our change is going to be affected. The investment and cost in waste management can be refocused to value generation. How? Any hours of operation beyond the designed rate of production is a waste of labor and energy. Any biomass not converted to final product is likely an underutilized value of the sunshine captured. Any energy expended as heat might have value to be pursued, and the packaging scrap that is landfilled likely has value to another business entity. How can this chaos be understood? Side streams and utilities can be shown better. We saw earlier someone who put together a Sankey diagram. They are the way of visualizing the chaos in the processing facility that moves materials and energy from raw to finished product and waste. Decision makers can focus on cases in and packaging. Side stream utility integrations fall through the crack. The status quo may bias and stifle CapEx that could recover value. These Sankey diagrams are an example of detailing mass and energy input and output. In this example, and it can go into it in what it says right there, but basically we have 1450 of raw material and we get 1,000 out. But we need over 5,500 kilograms of raw mass inputs if we figure our air and our water and other things. And it takes 33 gigajoules of energy per metric ton for the valued component. This is per hour or per ton. This thing needs equivalent of 220 gallons of gasoline per hour in order to run the process I've described over here. As companies are focused on the products their customers know or expect from them, the client's team may conceptually appreciate, but in practice not consider side stream potential value or operational cost savings. Some managers might, but it's a heavy lift to get through the CapEx stages. However, the project team needs to consider the side streams. If all that is expected from a customer is to send the whey off to the hog farms, then a U-shaped tank with a pouring system is the process. Add or do not add cleaning of the lines to the tank and the decision is complete. That may be all the client knows about handling side streams. The waste out of sight, out of mind, the cheese is the thing. Until businesses are forced by governments or several decision levels feel competitive pressures and potential profit, why change? Businesses can lobby, rebel against regulations, and governments and neighbors can place on their business. But as process designers, equipment suppliers, project subject matter experts, and academics, we see many customers and often can see a bigger picture. We can bring attention to upcycling, reduce, reuse, and recycle solutions. These, in the scheme of being profitable, may likely not impact the CapEx as the side streams generate revenue, save costs, and allow the business marketing team to sell a story of stewardship and sustainability. This leaves the question, what about the side streams, streams that are often considered waste, the non-commodity outfall? What about the integration with utilities? What about the available integration of government, research, technology industry with the producer team? Who notices side streams when the operations just work and costs are built into price? How often will personnel whose responsibility is to focus on side streams get a chance to speak? Will the decision makers in business, the marketers and financial people, go out to ask if side stream upcycle can have ROI? Anyway, sincere thanks to Dr. Lara Ramdin for crystallizing my thoughts here, and for all the associates of the Upcycled food community for bringing the forces that get us involved and paying attention. So the team there at Upcycled Foods, I appreciate your efforts.
Thank you, Stephen. Thank you for your philosophy on upcycling. I don't think you'll get any pushback from this particular audience. What's your ask of the people listening here, just as we bring this session to an end, day one to an end? What do you want to leave them with?
Day one to an end. No, you guys have been great. I was basically at some point I must have one of these imposter syndrome thing, looking at the talent that you've assembled and the speakers that have been here. But I've been in this industry a long time, and I can walk in and usually see so many opportunities, and I can actually express to people why the CapEx can be recovered quite quickly if they just put their focus on it. I have in the total presentation, I have another whole set of case studies. Probably, I think there's like 6 case studies. Biocatalysis of upcycled soybean oil for making sunscreen. I've got things on upcycling of in the meat processing industry. All the water comes in on the hoof, and yet they need 100,000 gallons a minute of water. And it's like, why are you doing that? You have it already on site if you just took care of it. And then CIP and cleaning, which is boring and nobody wants to think about it. That most of the water going down the drain is cleaner than the water they bring in from the city. A little's dirty, but most of it's cleaner. So we've got opportunities, and it's education that needs to get out so that it allows them to do so.
Well, thank you, Stephen, and thank you for bringing day one to a close. We appreciate your contribution, and we appreciate everybody that's on the line listening. We hope that you feel enlightened. We hope that you feel that your mind has been expanded. We hope that maybe we've introduced some interesting people for you to collaborate with. Most of all, of course, we hope that the upcycling movement continues to accelerate and continues to broaden and become bigger, and we all have a chance at accessing that potential revenue that we know is just right there. I know that, Amanda, are you going to do a bit of housekeeping before we talk about day 2? Or are you going to talk about day 2? Okay.
Oh, well, can't go to day 2 without sincere thanks for day 1 to you, Dr. Lara, for helping orchestrate all these minds that have helped contribute to each other's work, from beginning the day with Juan Jose, doing our deep dive with the Cornell team that was so generous with their time and expertise, David getting us caught up to speed, and last but not least, Stephen, thank you. I will hold that phrase, the is that it is, right? Thinking about what other possibilities can we help spark in mind. So such a great segue to what tomorrow is going to bring. So invite you, if you haven't already registered, grab the link at the code there. And we're going to do 2 journeys tomorrow. First, across Europe with Dr. Simona, who's been a longtime UFA collaborator, and then to Canada with Dr. Alexandra that we heard from last symposium as well. all sorts of topics that I already can tell align with so much we've talked about today. So really look forward to weaving all those threads through. We will be kicking off bright and early at 7 a.m. Pacific time and going for even longer than today. So all of you that stuck with us for so many hours today, thank you so much. Spread the word, invite your colleagues. Also, as a reminder, these will all be recorded and available for you to come back to and absorb because there's so much here. So definitely to echo what Laura said, if you feel inspired and sparked by anything you've heard today or want to keep working on together in community, we've got a seat for you, whether it's a $50 student membership, $100 individual membership, or for the academic institutions represented today, $500 to be a part of the conversation, and company memberships of all sizes. So really looking forward to thinking about this time tomorrow, how full our brains will be, but also thinking ahead to Upcycled Food Month, June 2026, and the 9 months we will have to plan to make this even bigger and better, and excited to incorporate your thoughts and ideas into that. So definitely, if you're with us today, stay in touch. Hope to see you tomorrow, or as you're listening to the recordings down the road. Much appreciation for everyone that pulled together to make this day really packed forward, and hopefully you're walking away with how you can play an even bigger role in the upcycling movement. Appreciate you all. We'll see you again soon.
Thank you. Bye.